Hello, we're about to start, about 1 minute. Welcome everybody. Hello everybody, welcome to the Yocto Project Virtual Summit. This is our second summit and our first virtual summit. And we're going to show some slides before we get started with the first presentation at 15 after. Welcome, yes, the schedule and the slides can be found at our pre-talks website. The schedule of the events, also for each event, you can find the attached slides so you can follow along with your slides. We've asked everyone to post their slides both in the native presentation format, but also in PDF. If there's any missing PDF files, let us know and we'll post those immediately. Basic rules, of course, please mute your phone and turn off your video, just so we can reduce the bandwidth for this conference to make sure everyone can see what's happening and follow along. We do have a channel, the Slack channel open. If you want to ask questions, of course, the chat session will be open in this window, but often we find that Slack is a more robust platform for sharing thoughts and questions and issues. But we'll be watching both. The presenters will be showing their slides. We'll be monitoring the chat sessions and helping out the presenters as they go. Before we start, I'd like to also thank all the volunteer expert speakers. We're all volunteers here in the Yocto Project and Open Embedded, and we're pleased to share our knowledge and our experience and really engage with the community. And we're pleased that you're all here. And finally, we want to thank Linaro and Linux Foundation for sponsoring the Zoom channels. This particular Zoom channel is sponsored by Linaro. The beginning class, intro class is sponsored by Linux Foundation. So we're very pleased that they're helping us out and joining us. And by the way, the links are the same we posted in at our booth in ELCE. And if you have any questions, again, connection issues, just post there. We'll be watching it. Class details, if you're taking the classes, yes, again, please mute while you're taking the class and when you're not asking a question. If you do have a question for the speaker, please raise the hand icon so we can catch you, and we'll look for those, and the host will see you and unmute you. If you have any general questions or comments, yes, again, please feel free to use the Slack channel. Our experts are indeed standing by. And for any technical issues, we do have breakout rooms. That's mostly for the hands-on classes for tomorrow. But yeah, let us know if you have any issues and we'll try to accommodate you. For the classes tomorrow, by the way, you'll need to request a pre-configured virtual private server. We have prepared servers for all the people attending the class. It's been pre-installed with the Yocto project. It's pre-inset each of the the 3 classes. So everything's set for you. And you just need to request a virtual private server, and our expert, Michael, will send you your credentials to log in. You will need SSH on your computer to connect. We've done this class from Linux hosts, from Mac hosts, from Windows hosts, from even one person did their class on an iPad somehow. So very impressed with that. But yes, just need SSH. And if you have connection issues, of course, check your firewall settings to ensure that SSH is working. The sooner you get your private server account, the sooner you can test it and let us know if you have any connection issues. So yes. If you need more direct help, yes, again, raise your hand and our host will temporarily move you to the Zoom breakout room, and where you can share your screen, talk to them, and they can figure it out. And there's always going to be some people with little issues that we didn't anticipate. Sometimes the clones don't quite work when we clone the images, and Michael will be able to very quickly help you out, maybe give you a new credential, a new machine, and he'll get you going. And with that, let me then pass on to Nico.
Hello, everyone. This is Nicola, I'm the Yocto Project Community Manager. And yeah, I wanted to share some updates with everyone today on the Ambassador Program. So the Ambassadors Program is a community initiative that we have on the Yocto Project, where we recognize individuals that are doing really good work to actually show the project and talk about the project, or basically, I mean, around themselves. So we've launched that a few years ago, and we have, I mean, some ambassadors have been recognized, and I'm very, very happy to share today that the Yocto project has decided to nominate a new ambassador. So Ito is a community member. He's based in Japan, and he has been doing a lot of work in Japan, and actually especially in Japanese language, to help promote the Yocto project. He's teaching Yocto in Japanese language. He's speaking at many technical conferences in Japan. And that's something we've been discussing a lot lately, but how to reach out to countries where English might not be, I mean, the best language to use. So as you know, all the documentation from the Yocto project is in English, and sometimes it's a problem. So we really value the help we can get from people around the world to help us talk about the project in their own native language. So we have few people that, I mean, like we have some representative in, I mean, we talk about the project in Italian, we have German, so we have, I mean, hopefully we'll see more and more of that. So I'm very happy that Hito, what he's doing in Japan, and very happy to have him now becoming an official ambassador for the project. We'll be posting all the information on the website soon. So thanks, David.
Okay, we've completed our introduction in record time, 7 minutes. The first class will be starting at 5:15 Pacific time in about 7 minutes. So if anyone has any questions, you can raise your hand. We're looking for the links to post into the chat for the self-registering into the Slack channel. Yeah, I posted that at the booth at the Yocto project. I think the booth is still up. I think you can still enter that and pick that up. If someone could post it, I'm presenting at the moment, so I can't go away from my screen. If someone could also post the link to the schedule and pre-talks, that'd be great. Oh, okay. Andrea said that the link that Paul sent was working. And there's the schedule. Thank you, Nico. So I'm going to go ahead and download the first slide. And make sure you're on, say hello to us on Slack. I see that Andrea has posted the coffee icon. That sounds good. I'm going to get this set myself. And Jan Simone. Yay, coffee. So HG, I see you raised your hand. Did you have a question for us? Hello, HG. Did you have a question?
Just to answer the question on the chat, the slides are on the schedule. So if you go to the schedule page, and each session, you will be able to download the slide, assuming we have received the slide. And yeah, otherwise, every presenter will just show the slides during their talk.
To get the link to request a VM, we did send an email blast. Hopefully you will receive that from the Linux Foundation. Otherwise, you can download this slide from the P-Talks and click on it directly from there. And I'll post that link as soon as I stop presenting.
Just drop that link in the Zoom chat, David.
Excellent. Thank you. Thank you, Paul. Okay, about 3 minutes before we start our first presentation.
David, I think the schedule says 12:10, not 12:15.
Oh, I am very sorry. Then let's go ahead and get started. I will stop sharing. Okay, Bruce, it's your turn. Go for it.
We don't hear you, Bruce. I don't know if you are. We are muted on Zoom, at least.
All right, now I think it's working.
Yeah, now we see you. We have the slide and we hear you. So.
All right, sorry. I should have tested this, but I was working on the kernel lab yesterday. I didn't get a chance. So I will catch up because this is sort of the not interesting to start. I'm going to talk about building and deploying containers with better virtualization now and in the future. It's a variant of the talk I gave at in Brussels after FOSDEM. I kind of renamed this in my mind this morning. It could be called 8 years of deploying containers, and it sort of works now. So that's the new title for the presentation time I do it. I'm going to cover these two parts, really the first part's quickly because I started. I moved a little bit of what was in the description of the talk on the site, just because there's some other are probably going to be concrete and better examples. So I did not do an actual cut and paste build and deploy of a container. You can find that in actually some of my old, if you're that interested, or a week at another time. What I'm trying to cover in this talk is actually to introduce some of the concepts that are driving the container build and deploy. As I mentioned, it's not a how-to, and it's not strictly a survey talk. So I'm not just going to go over all the options and list what you could find by going and repositories yourself. I want to level set on some of the history, why things, that helps explain why things are how they are. Do a little bit of background and understanding of the current capabilities, what, why,
Hey,
and how.
Both, sorry to interrupt. There are various reports that sound is not coming out quite well from your side. Everybody's muted, so it's not something that, some echo that comes from us, but it's a bit choppy and with a bit of echo. So
yep. The best laid plans, right? I'm not sure. 1 sec, I guess. Hold on.
And yeah, sorry about that. That's not the best way to start, but hopefully it will just get better.
All right, does this sound any better?
Yeah, that's much better. Thanks.
All right, so just a sec. I went to a headset, so that should hopefully everybody can hear me better now. Recap. Forget it. We're just gonna go to the talk because everyone see the slides. That's what I'm gonna do right there on the presentation goals. So a quick overview. This will be really brief. It'll be a minute now instead of the 2 minutes or 3 minutes I started. So meta virtualization is actually since June 2012. We're now over 1,300 commits, 55 different contributors. It's sort of a point of integration for quote unquote virtualization technologies.
I'm sorry, boss. It's not better actually. It's still the same. Someone suggests that it might be your camera feed or some bandwidth issue or something else. David, should we?
I draw video. Go do without video. Is that any better?
No.
Huh. Of course, it hasn't been a pro week, and now it is.
Perhaps you need to rejoin. Maybe Zoom is messed up for your connection.
All right, I could try that. We'll give it a go. Hold on.
Sorry, everybody. This did not happen during dress rehearsal. And we all tested this, so part of the excitement and fun with Zoom.
All right, test. Before I even start resharing, does this come through any better or not?
It looks like it is, but it looked better also earlier. I mean, you need to speak a little bit more.
Like I say, if this doesn't work, we can we'll just flip to a different presentation, and maybe I'll try to find a different way to get.
Yeah, that's same. I mean, you will watch the video, so you will see what we hear, but that's not good.
Yeah. All right. So it's no better right now, even though now that I'm talking a bit more. No.
Yeah, no.
All right, we can go with a different talk then. Clearly, my band wrong in my neighborhood with my with.
Okay, so David, should we pull the next?
Can Bruce just call the 800 number on his cell phone?
That would be good.
I'm
Bruce,
already
you still?
I'm too far into my slot. We can just people can just read my slides at some later point. That's fine with me.
Actually, Bruce, why don't you try to call in with your phone?
I don't have anything near me, so it'll take too long.
Is there someone else who could speak to your slides, Bruce?
Maybe he went to get his cell phone.
Ah. So what we'll do is we record this presentation and have it available on after the conference, so we can all get Bruce captured in his full glory. In the meantime, I think we're trying to get a phone and try to figure that out. The second presentation was Docker containers, and that is given by, who is that given by?
Sandra.
Sandra.
Now we are early, so I don't know. Sandra, are you online? I see you, Sandra. You should be able to unmute.
Hi.
Sorry about the last minute change, Sandra. We had some issues on the first session. Do you think you can start yours? We'll probably just extend the next break to cover that we won't change the schedule for the whole day. So we'll do this presentation, the next one, and then have a break, slightly longer.
Okay. Can you hear me? Is it okay?
Yes, we can.
Okay. When do I start the presentation? Now?
Nico, are we ready?
Yes, please.
Okay. Okay, so good morning, everyone. I will present you a short presentation about integrating Docker containers in the Yocto project. Is it okay, the sound? Everything is normal?
So far, yes.
Okay, let's go. So my name is Sandra Tobajas. First off, I would like to ask you all to please be patient, as this presentation is entirely in English and English is not my mother tongue. I am currently working as a product engineering consultant at Savoir-Faire Linux in Montreal. In the past couple of years, I have worked on different projects with customers using completely different business and industrial contexts. And some of them came to us saying, "Hello, I have a new board and I would like to embed my legacy application on this new board. Can you help us?" So as their presentation development was out of our scope, my team and I began to think about how we could help them to integrate their application into their new BSP. Many of those projects were built with Yocto, but the system design would have been the same with another build system such as Buildroot, for example. To continue with my little story, we started to figure out what would be the benefits of running containers in embedded systems. Over time, many questions and issues had been raised during our brainstorming, as we are always trying to align the customer's needs with the reality of the production and industrialization of their product. After the brainstorming, we started to experiment some approaches with Yocto. We came up with two approaches that I will describe during this talk. Most of the time, customers come with their own applicative stacks. For example, one of them had a Qt HMI application based on Ubuntu, and the other had a swarm of services acting as a web server and was based on an Arch Linux distribution. So the main goal of the containerization is to decouple the application from the base operating system. You won't need to install some specific distribution package the application relies on, or a conflicting library that would pollute the Yocto BSP. To achieve that, the interfaces must be specified between the base system and the container. These interfaces can be hardware resources such as audio, rendering devices, shared storage volumes, or even network-related resources. Furthermore, this allows the developer teams to focus only on the application and ignore the platform specificities. With a set of defined interfaces I have listed earlier between the container and the platform, it brings the ability to run the application container either on a developer machine, a continuous integration pipeline, or a production machine. This allows different update cycles regarding the base system and the application. Nonetheless, application and systems teams must ensure that interfaces are always current. Here is a short list of the benefits of running one or multiple containers in an embedded system. Running containers provides isolation of the application through namespaces and many other Linux mechanisms. The overhead in terms of memory consumption, size of the image, startup time is also lower than virtual machines. At this point, everything seems to indicate that running container on embedded systems is a clean solution and should be implemented everywhere. However, that will be too good to be true. Integrating a container brings up relevant challenges that apply in the industrial and embedded world, and they have to be addressed during the product design. Some of these challenges will not be detailed in this presentation, as they can be a whole separate topic of discussion. So in this list, some of the challenges are tied to the embedded context and other to product engineering and commercialization context. The first obvious challenge we can think about when talking about embedded systems is a limitation on hardware resources. Sometimes the devices do not have enough storage capacity, hardware resources, or RAM to run a container based on a full distribution. Even if the containerization has nearly the same performance as an application in its native system, we have to keep in mind that the container is often based in a full distribution system, and this can add some overhead. The traceability and reproducibility of containers is an important challenge, as the deployment pipeline can sometimes break. Finally, the management of software licenses is another challenge. Complying with license requirements is essential because it minimizes business and legal risks. Yocto has already a mechanism to track and maintain compliance with various open source licensing tools during the lifetime of the product. So the compliance can be done at the system level. However, it does not exist for an integrated container into Yocto build system. To continue with my little story with our customers, part of these requirements are quite common. They can be divided in two parts, the target and the build. The target board has often no connectivity, and the root file system has to be immutable, set up as read-only file system. Also, the boot chain integrity can be verified to ensure that all the ports of the boot sequence are not corrupted. Here you can see a simplified system layout with 4 partitions. The rootfs is a squashfs image and contains the Docker engine and the Docker images. We consider the data partition as disposable. It means that if a data corruption is detected on this partition, it can be reset to factory. From the build system, the Docker images are already stored in a registry owned by the customer. To ensure reproducibility on the build system, Yocto must be containerized. Internally, for all the project, we use security, a small wrapper we built to facilitate running containers commands that maps the current directory in a project-specific Docker container. The Yocto build system is containerized, but the Docker image has to be integrated in the root file system during build time. Indeed, the container engine must be installed in the build environment. Neither Docker nor Podman have their recipes available as native tools in the meta virtualization layer. In our case, the container engine will be installed in the build container. However, a solution such as Docker in Docker or Podman in Docker has to be integrated into the build process as well as Yocto and brings several concerns. As I said earlier, data corruption is a major cause of embedded device failure, and it is a recurring concern among industrials. Actually, setting a read-only root file system is our practice by default when designing a Yocto BSP. Indeed, data corruption can cause unexpected system behavior even if only one bit is flipped. The temporary data that needs to be written by the container engine can be stored in a volatile or non-volatile writable file system. The difference is that the data will be written once again at each boot or not. But this data is still considered as disposable if a corruption is detected. Therefore, some countermeasures can be integrated to detect such corruptions. In the best case scenario, the system can be able to repair itself after detecting such corruption while maintaining file integrity for critical and embedded systems. The boot integrity verification or mirroring critical partitions can be part of these countermeasures. In the first two sections, I have explained the context and the challenges related to embedding a container image into a Linux embedded system. Now let's talk about Yocto and how we have integrated this solution into Yocto. I am convinced that our approach is not the only way to embrace the problem. With that in mind, I will explain the concept and then I will show you the implementation details of the meta layer. Two approaches stood up from our brainstorming. The first is to embed a Docker archive in the root file system, and the other is to populate the Docker store into the target root file system. To be precise, I will call the Docker store the varlib Docker directory. The Docker stores contains information such as data for container layers, volumes, builds, network, and clusters. The meta I have developed gathers all the components needed to build a simple system image. The meta embedded containers layers is available on Savoir-Faire Linux's blog, GitHub, sorry. The distribution configuration file is based on Poky and adding the following features: virtualization and systemd in the system. We will have to add some host tools as Docker or Podman. It allows some external binaries that are not native in Yocto to be called inside a recipe. In the image recipe, the container engine is installed on the machine, and the image is a SquashFS image with read-only rootfs image feature. As the root file system is read-only, rootfs post-process command allows the Docker engine to be writable, updating dynamically the fstab file regarding on the use recipe. Here, the update fstab archive function, the varlib Docker directory will be bind mounted on a temporary volatile directory. Now I will focus more on the container archive recipe, precisely which will embed one or multiple archive files in the root file system. Several files can be shared in common between the three recipes and the two approaches. The next step is to put everything in common in one class. All the container images I want to install on the target are listed in this manifest file. I have to specify the image name with its registry, if there is one, the tag of the container image, and its local name once the image is installed on the target machine. The container archive recipe is divided into 3 custom steps between the do fetch and the do install task. First, pull all the image along with their tag described in the manifest file. Here, podman is used to pull the container image. Secondly, we tag the container image with their local name described in the manifest file. Then, the container images are saved into tar archive files with the podman save command. The storage driver here is overlay to allow bigger image to be saved. Finally, install the archives files in the root file system. In the installation task, the recipe will install the systemd service that will load and run the Docker images. Considering this approach, Docker or podman can be used during the build time to pull and save the Docker image into tar archive. Then, once we have flashed the image on the target, during the boot time, the Docker engine will be present in the root file system. So the steps will be: first, mount the Docker store in a writable partition in order to run the Docker daemon. Start the Docker daemon, load the Docker archive, and finally, run the Docker image or multiple image. The Docker store can be bind mounted in a non-volatile writable file system. The docker load command could be performed only once as a first boot or when the writable partition is cleaned. After the Docker daemon is started, the container archive systemd service can be started. There are 2 steps. First, load the tar archive with the docker load command. This is done with the container load script. And then once the Docker image is loaded in the local Docker registry, it can be started with the container image script. The docker load command can take some time to perform. Just as an example, it can take around 1 minute to load a Docker image of 2 gigs, depending on the machine hardware specifications. Finally, we can see that all the images present in the manifest file have been started and run by Docker. A variant of integrating container archives approach can be set with Docker Compose. They are the same steps as the one described for the container archive recipe. It means that all the container image archives files will be embedded in the root file system. However, we have to install additionally the Docker Compose configuration YAML file and a quite modified starter script. The systemd service will load the tar archives files and then start the container swarm using Docker Compose up and down commands linked with the embedded Docker Compose YAML file. Furthermore, the Docker Compose YAML file will point to the local names of the container images loaded in the local Docker registry on the target. Now I will focus on the approach that populates the Docker store in the root file system. As the first approach, the update fstab image root fs postprocess command will update the fstab file to mount varlib docker as an overlay fs. In the container image recipe, we will have the do pull image task that will first off check if the Docker daemon is not already up and otherwise kill it. Clean the Docker store to have a fresh start. Start the Docker daemon specifying the control Docker store path with the data root option. The Docker store set by default is varlib docker, but we want to control our own fresh clean Docker store. Furthermore, the use storage driver is VFS, as the Docker store will be mounted as an overlay file system on the target. And as a nested file system that offers unified views such as overlay over an overlay FS is not supported by Linux. Then, once the Docker daemon is started, we can pull all the Docker images described in the manifest file with the docker pull command. And finally, clean the temporary directories as they will be created on the target system. At the end, we kill the Docker daemon. After that, I am able to install the control Docker store in the target root file system. Here. But BitBake will analyze all the file and binaries installed by each recipe during the do package task. For each file located in the package, BitBake wants to link those files to an existing Yocto package or recipe. However, we don't want BitBake to analyze and add all the container-related stuff in the dependencies. So we will skip the QA packaging. And we will also trigger the shared library resolver to exclude the entire package when scanning for shared libraries. This can be done by using the exclude from shlibs variable. During the boot time, the Docker store has to be mounted as an overlay FS on a writable partition. Then launch the Docker daemon and finally run the container image. As the Docker daemons run on top of an overlay FS, we have to consider on how the Docker image has been pulled during the build time. The storage driver defined during the build time will define how the container layer and data are organized during the pulling step in the Docker store repository. Here, the Docker daemon can figure out automatically which storage driver has been used following the layout of the container layers in the Docker store. The container image systemd service only runs the already loaded container image. The boot time is faster with this approach, as we don't need to previously load the Docker archives file. Many container engines exist, but we want one able to deal with the Docker image format. Podman and Docker are able to handle several types of container archives using podman save or Docker save commands. As I said earlier, this consideration happened only because our build system and process is containerized, and we have to face Podman in Docker or Docker in Docker problems. Nonetheless, the choice between Docker and Podman happens only for the approach integrating Docker archives. Here is a summary with pros and cons of both solutions. Both can work. The main advantage of Podman is that the tool is standalone and rootless, and sudo privileges are not required. But I had issues to run Podman in Docker with a version newer than 1.5.1 in a Docker container. On the other hand, Docker needs sudo privileges and the daemon has to be started before pulling the image. Finally, here is a summary of both approaches. The main difference between both approaches is the boot time. In the first approach, you can have the choice between both container engines, considering pros and cons I have listed earlier. The Yocto integration is also easier as only tar archives files need to be installed on the root file system. On the other hand, the second solution minimizes the boot time and the amount of writing operation, as the Docker images do not have to be loaded. The integrity of the Docker image are ensured during the boot and runtime for the second approach. To conclude this presentation, I would like to share the articles I have written of this topic present in the Savoir-Faire Linux's blog. Also, the meta-embedded containers is also available on GitHub. It is a minimal layer and can be improved. The approaches we proposed are not entirely based on Yocto, as we are installing and using Podman or Docker in the build system, and not using them as native tools. It could be possible to integrate them natively in Yocto. The integration of the container license compliance can be another way to improve this approach. Furthermore, our use case is based on container images based on a full distribution. The images are stored in a AL registry we don't have access. These customers' requirements have driven our approaches, but I am still convinced that is not the only way to embed container images into Yocto. I would like to thank you for your time.
If there are any questions, please raise your hand in the chat session. There was an earlier question about containers within containers. I think Docker within Docker.
Yes?
If you could speak to that.
I didn't understand the question, sorry.
I think you mentioned running Docker within a Docker instance, or someone asked that question.
Do you want me to speak about Docker and Docker integration?
Yes. In what instance would you run Docker within a Docker instance?
But on the build system, the Yocto build system is containerized in Docker in our part, and the Yocto recipe needs to pull the image. So Docker, I need to install Docker in a Docker. So my Docker in Docker solution works on my build machine, works on my CI pipeline also. Does
Okay.
it answer to your question? I'm not sure.
Yes, I think part of the question was, is there a use case for Docker on the embedded target or Docker in Docker?
No, on the embedded target, it's only the Docker. And the embedded target is not does not have connectivity, so just Docker is fine. We cannot pull from the target.
David, I have a question. I don't see how to raise my hand, by the way.
Go ahead and we'll figure that out. Randy?
Okay. So, nice presentation. Thank you. You mentioned, I think, sort of a 1 minute startup time for the container on the target. Can you talk about how that compares to a containerless solution and the cost benefit analysis of containers versus native software?
Okay. In the first slides, this was this one. You want me to compare that the Docker approach versus a native one?
Mainly around startup time, because I think I heard you say that your startup time within the container is a minute or more, which can be a problem for some embedded systems.
Yes, but the customers have the requirement that their application has to be containerized. So we started from this requirement.
I see. Okay.
And the customer also has dependencies on distribution libraries and applications. That's why we don't have to, we didn't embed the application as native in the target system.
Okay, I must have missed that. Thank you very much.
Okay.
So Mattia asks, are there alternative solutions besides yours for running Docker containers on the embedded target?
I just said in my conclusion, I think it's really depending on the requirements you have here, because we came with these approaches because our customers, we had some requirements from the customers and from our build system. But I think that other approaches can work, and maybe the following presentation will explain more approaches, I think.
Okay. There are 2 hands raised. So Ms. M. El Shahawi, why don't you go ahead and unmute and speak?
My question was about the Docker on Docker, but Sandra already answered this question. So thank you.
Okay. Do you have a bonus question? I guess not. Okay. Dan, why don't you go ahead and you have raised your hands. Why don't you go ahead and unmute?
Yes, can you hear me?
Yes, we can.
Great. Thank you very much for the talk. Very informative. I wanted to ask a question about, I noticed that the example was showing mapping your varlib Docker directory to tempfs. And I was wondering if I can understand reasons why you'd want to do that, but I was wondering if you needed to handle cases where you had persistence, either persistent containers or persistent volumes mapped to containers, and whether there were any challenges associated with that, if you've done anything with that.
Yes, here in the meta layer I have developed, I put it in the tempfs, but for the customers, we have put we have loaded the images in the writable partition, the data partition, and the load of the container images is only is done only once at the first boot, and then the data is persistent, and during the lifetime of the product, if the system detects such corruption, we agreed with the client that we can flush the data partition and restore the data, loading another time the Docker images. But the concept is the same that the TempFS I have described. This is just an example.
Okay, good to know. Thank you very much.
You're welcome.
Okay, to raise your hand, you open up the participant list, and then at the bottom of the participant list, you can see various icons for raise hand, yes, no, go slower, go faster. I mentioned that because someone mentioned in chat that they may not see chat to know how to raise their hands. And Randy has his hand raised and dropped.
I just wanted to let you know that I found the icon. Thanks, David.
Well done. You get a sticker.
Oh boy.
Okay, do we have any more questions? Manuel, go ahead, please unmute.
Thank you. I hope you can hear me.
A little bit louder would be great.
Okay. Give me a sec. I'm sorry. Okay, I'll do my best to speak loud. I hope you can hear me properly. I just wanted to ask, like, you have talked about two ways. One is having a tarball on the deployed target, and the Docker loading that at runtime. And the second one is that you basically, if I understood you right, you already pre-populated the varlib Docker directory on the target, so you do not run have to run Docker load at boot time. But I'm not really sure if I got this right. Can you perhaps elaborate on that?
Yes, of course. I will show you the slide here. Do you see it? When
Yes, I do. Thank you.
Yes, it's a copy of the directory. So in the first, here we started the Docker daemon with that Docker store, control Docker store. We want to put all the images. We pull the images we want to pull. And this populates the Docker store. And then during the install, I just copy the Docker store directory in the target root file system.
Okay, I see. Thank you. And I'm not an expert on the VFS file system, but I think that's a layered file system as well. So am I right that you are you using kind of two layered file systems, because SquashFS is kind of layered, I think, and then on top of that you've got the VFS. Is it correct, or did I get this entirely wrong?
In the target root file system, I have varlib Docker, and I need to be I need this directory to be writable on the target, so I mounted it as an overlay, and that's why I pull all the image as VFS, because Linux does not support overlay over an overlay FS on the target. That's why I have to pull the image during the build time as VFS. The structure of the layer will be different, will be stored as VFS layers into the Docker store. And then on the target, Docker will figure out how the image have been pulled and will recognize the VFS storage driver. And so it will you see in the Docker logs, Docker will try overlay. No, my image are not pulled like that. The architecture are not like that, and Docker daemon will recognize the VFS driver, and that's why I have to use VFS over LFS.
Okay, I got you. Thank you very much.
No problem.
Okay, Sean, you have your hand raised. Why don't you go ahead and unmute? Oh, disappeared.
Hi, can you guys hear me?
Yes, we can.
Yeah, thank you, Sandra, for the presentation. I'm just curious if you can, let's say, divulge in some information about the target system that you have. So, for example, how much powerful or how or what are the specifications that probably might be needed for your present applications as well as for the future applications, like what would be the RAM specification, what type of board would you be able to deploy such kind of containers on? Because I think, from my opinion, it's sometimes Docker gets really big on embedded devices, and then it's good to know what kind of target boards would probably suit best for such kind of situations. Thank you.
My machines are nearly as computer performance. The both machine I have tested this approach. There were x86 machines with a Core i7, if I remember. I don't know how much RAM the machine have, but between I will say 8 gigs minimum. 8 gigs. It's quite a big machine for an embedded system. I didn't tested this approach on lower specification machine, but I think that it need to be tested. Ouais, mais c'était pas la même.
Okay, so just to be clear, maybe if you, for example, if there's someone out there who's looking into the GitHub repository that you mentioned, it's probably possible to, let's say, use a Raspberry Pi 4 with some decent 8 gigabyte RAM, and then maybe this thing might work out on the board. Is if that's what you're trying to tell me.
Sorry, I didn't.
So I understand, from what I understand is you're using some generic x86 machines with some
Yes
8 GB RAMs. But if someone wanted to use the code that you have mentioned on your GitHub repository and then port it to, let's say, a Raspberry Pi 4 or a decent embedded board, it should be able to work, right? That's from.
I think in Raspberry Pi it will work.
Okay, yeah, okay, thank you so much.
Okay, any more questions? Please raise your hand or post something to the chat. Okay, Sandra, I think very good. Thank you very much. I think that's
Thank
all our
you.
questions. Excellent. Okay, we'll take a moment and then we'll start the next presentation. Okay, the next presenter has recorded his presentation, and Nico will bring it up in just a moment.
Right now.
So as David said, Robert is with us today. So hi, Robert, but he has recorded his talk so that he can also answer questions during the talk. So we will have 2 Roberts today. We've tested that and hopefully it will work. So I will soon, whenever you think it's time, David, I will try to start the video. And Robert, yeah, hopefully everything will go fine. And the backup plan is that Robert will just do the talk live, but hopefully the video will just work. So David, whenever you want, I can try to start.
I think we can go ahead and start. Give more questions, time for questions after.
Hello, ladies and gentlemen, and welcome to OCI Docker Containers with Meta Virtualization and Open Embedded Yocto project. Another containerizing the planet talk. So, after a brief introduction, I refer to some previous talk. You might watch this as well in order to understand certain concepts which I will not show again in this talk. We have a look at some requirements, what we're going to try to achieve here, and then we look from top down, starting by top level configuration files like localconf, bblayers.conf and friends, multi-config as well. Then we look briefly into Docker, into container standardization, which brings us to OCI images, and at the end we see how those could be embedded into our root file system, and then some further work I'm trying to look into as time permits. So that's my business card. My name is Robert Berger. I'm an embedded software evangelist. Email, phone, and my website. So this is how you can reach me, and in case you would like to have a virtual meeting with me, just use this link down there and we can set up some convenient time slot and have a chat. So what am I into? What's my business? Well, there's consulting, mainly around Yocto project, embedded Linux, real-time stuff. Training, a significant part of my business comes from there, and teaching is a great way to keep learning. So, well, as you know, you never stop learning. You ask me questions and I'm trying to figure out how things work. One training which is Yocto related is this one, the Yocto project thorough overview, which is 4 days long, and these are the next public remote sessions in this year. And another Yocto related training is this one. It's 2 days refresher to embedded Linux, followed by 3 days of Yocto project. And the first of these 2 dates this year, so 16 to 20 of November, is already guaranteed to run. So far with a German speaking audience, but they are fine with English as well. And I do also some engineering, mainly for automation and other things I need for my own business. Here you see these are customers I trained, and it's a pretty broad bandwidth, as you can see here. Now, this is the reference to my previous talk. Have a look at it here. Here's the YouTube link to it. Yeah, I talked about some use case and hardware software for it. Golang and issues I had with Golang and how they were resolved, how to get the applications packages onto the target, how to get Docker and related packages onto the target, how to get Docker Compose onto the target, and how to build an OCI container and get it on the target. Well, in this case, I used the registry. Therefore, now, what are the requirements? What we try to achieve this time? Let's say we want to create a root file system which is able to run some container, specifically Docker container. Therefore, I use my distro called ResiWord, and I install Docker Compose and systemd, which is required by Docker, and the kernel is configured in a certain way, so Docker is happy with it. This is the application container, so this is what ends up in the container, and it's also the container itself. The distribution for this is called Resi container, and what I'm doing here is I build an OCI container. So with meta virtualization, we can do this out of the box. Now, in my previous talk, I described how you do this, and I will show it also a little bit here. So you can build an OCI container on your host machine. You can push this to some Docker registry, and then on the target, you can pull it from the Docker registry. And well, like this, you get the container onto your target, and you can run the stuff. Now, a topic came up last time, which was how would you bundle this application container into your image without using the registry? And I was, of course, intrigued to figure out how this could be done. So I said, okay, let's try to use multi-config. And with multi-config, I can now build both this root file system, which is able to run Docker and friends, and I can also build the container, the OCI container. Now the tricky part is then how I embed this container in the root file system. And let's assume that we could just build a package. So let's assume we can take our application container and make out of it a normal package, and then we just install this package in the root file system, and like this we don't need a registry anymore. And let's also assume that systemd and Docker Compose and friends take care about the startup and other things which are required here. Alright, so top level configuration files. Apparently an important file is bblayers.conf, and you see here those two are standard POKI. This is my stuff, so these two are basically the BSP. I split the bootloader and the kernel into different layers, which makes things a bit more flexible than having them in a single one. Here is my own distribution, among other things. Various meta open embedded layers, meta virtualization needed for OCI containers, meta-dig, so this is Telegraph, InfluxDB, and Grafana, and we look at the Telegraph part here, and MetaPython2. Oh my god, MetaPython2. Well, the maintainer of MetaPython2, Tim, says don't use it. If you want to use it, you have to maintain it yourself. So I got rid of it. I was lucky. Meta-dig, my own layer, needed it, one recipe in there, and I just replaced it with Python 3, and it worked. So yeah, no worries. It's not always that easy. Now, a part of the local conf looks like this. So I define here some machine. Here I say in case we build a container image, app container, we don't want this U-boot UNV helper stuff inside, which is basically the U-boot environment. Here are two machines defined. So it's this one, which is the one for the root file system, and it's this one for the app container. And also what I'm doing here is I mask out certain subdirectories in case I'm building a container. Then I don't need, of course, all these recipes, BSP and recipes kernel stuff. So I remove it from here. And the last line here is I tell it, please load for me this BR filter kernel module in case I do not build a container image, but the real root file system. Here are the two multi-config configurations. So this is the root file system definition. So it's this machine, this distribution, and this is where the temp files end up to. And this here is basically the application container. Again, a different machine, a different distribution, and a different directory where the temp files end up. Now, pretty much the same as last time. What we see here is an image which contains Docker and Docker Compose. I take a core image minimal and add those things there, and some tools for convenience as well. Now, if we look at the Docker software stack, we see that in user space we have here Docker client and Docker Compose, and we might have a registry, well, typically not on the target, but somewhere remotely. And if we wanted to expand all this from a single board to multiple boards, we could use Docker Swarm or Kubernetes. And the Docker engine is in my case Docker CE, the community edition, which is based on certain open source technologies. From the kernel side, we need namespaces, C groups, copy and write storage, and we could use a few more if we wanted to harden the system a bit further. Now, let's say we just wanted to build a root file system without the application container. So just a root file system with Docker on it and Docker Compose as well, and no container yet. So let's see the container separate from this. This is how we could do it. So in the multi-config configuration, we could say for this machine, this is what we would like to build. All right. Now, this is just for you to have some references about OCI, container standardization, the image spec and the runtime spec. And the reason is I will use OCI images. We'll see further on how this works. Here I'm trying to explain briefly the concept of microservices. So the idea is to have one application in one container. You see here we have the container runtime, and we might have here a telegraph container. And although all the rest here is Yocto stuff, we could have here Debian 9 dependencies in this container, which is a pretty cool thing. The kernel is the same. So how can we do this now in Bitbake and recipes and friends? We need a minimal root file system without the kernel. So all this was inspired by a talk by Scott Murray. You can have a look at it. Here's the link, 2018. And we need meta virtualization for OCI support, and we need Scopio in order to push the application container to some registry. I use a host container for this as well. How does it work? the app container image telegraph pre-built OCI recipe. Looks like this. It's just a wrapper, as you can see. So what I'm doing here is I say, if I use meta virtualization, then include this thing here as well. And we need some app container image telegraph pre-built common inc file. Now what are those? The common inc file is just this one. So in this container, I just want busybox and telegraph and nothing else. And the other file I showed you before is a generic file which I always use with my OCI containers. So you see this includes some common image inc. We'll see what this thing is. It's not important here. But this is important. So we need image fs types container and OCI. This comes from meta virtualization. And we inherit here image and image OCI. And we tell it not to include any kernel in this case, and install here some base files, base password, net base. So this is what I took from Scott, this here as well. Now the other magic file, this one here, does nothing else but this stuff. So this allows me to see when it was built and so on and so forth. So it's not important for the purpose of this talk here. Yeah, so again, in multi-config, we could build now only the container. So we could do something like this. Multi-config for this machine here, we built this image, and then we can now, what comes out of this, we can push it to some Docker registry. So what I'm doing here is I unpack the result of the previous build, and I do is copy, and I copy it around to some Docker registry. You see here, this is my Docker registry, you need some password there, and then it pushes it up to the Docker registry. Reliable operating systems, OCI, telegraph pre-built, and I give it some tag as well, and I think I give it another tag with latest and this one. I'm doing also some other magic. I compare the remote checksums with my checksum here in order to see if they are really identical, and I'm doing this also before, so I don't push things which are already loaded to the registry. Now once we did this, we could try on our target to do a Docker pull just like this, and this is gonna work actually. So on my target, on my embedded board, I can do a Docker pull and all this stuff here, and then it's actually gonna pull it, and then I could do a Docker run, and it's gonna start up Docker. And if I, like this, get into the container, so you see entry point bin edge, so I open a shell in my container, I actually find now telegraph in there. If I try to run it, it's not going to work because it needs some further configuration, but this is just to show that we can build a root file system which is able to run Docker. We can build a container, we can push the container up to some registry, we can pull it down on our target, and this actually does something. All right, so this now is a very interesting idea. So let's imagine that the container is just another package. Yeah. It's a different distro than the target root file system, but anyhow, the Yocto project has multi-config to deal with those kind of things. So multi-config is also used to, I don't know, if you have a heterogeneous processor, to build a Cortex M binary blob in multi-config, load it onto the root file system, and then somehow transfer it from your Cortex A to the Cortex M. Yeah, but I'm trying to do something similar here. Yeah, we could have even different compiler tunes and stuff if we wanted to, of course. I also played with this, but okay, this doesn't make much sense. This is just for fun, because it's the same machine we're running on. So, what I'm doing here now, I create here a new recipe, core image minimal word, Docker C Telegraph prebuilt MC for multi-config. And I just take the file from before. So this is basically the root file system we had, which contains Docker and Docker Compose and friends. And this now, let's say, is the application container as a package. So let's see how I did this. Well, that's now the recipe for this application container thing bundled as a package. I have too many variables here, of course, but you see what's going on here. So the container machine is this one, the distro is this one. Here basically some paths are described here where things should go. The tarball, which finally gets produced. And this is interesting, line 28. Yeah. So what does this do? I described it down here. If we bit bake this one here, yeah, this is the root file system plus the container. So if we do something like that, then it builds both of them, basically. And it says it also depends on this one. So what I'm doing here is I say, okay, build for this machine this image, and this image, which is basically this one here, yeah, depends also on this stuff. And what is this stuff? If we expand it, then this expands to our container image. Yeah, and basically the task on which it depends is to image complete. So basically with this magic line, I tell it, build first my container image, my application container, and then, so this is a prerequisite, and once this is built, embed this also, which is what I'm doing afterwards, into my image. How I'm doing this? Well, I'm doing it here. So what I'm doing here is I say, okay, the build result of the application container ends up in here. Don't unpack it, just take the tarball into your source URI. Now what are the other files here? We're going to look into this. So I say here, okay, I have here some magic wait for file. This is used by Docker Compose YML. So it's this one here to wait for some log file. Yeah, so this is now Docker magic or Docker Compose magic, how you can wait for some file and not exit with an error. And I also have some other things here. So I have here some create influx DB name, and this again my script, and this script needs then some device identity, which is a file which creates some unique string per port, something like this, and a Telegraph conf file, which is some initial configuration for Telegraph. All right, the YAML file, so the Docker Compose YAML file, this one looks somewhat like this. So we define here how the Docker image is called, what's the name of the container, then some ports, which I expose. So port 8000 is exposed to 8079. Various volumes, which means what's in the container. One of those strings is the other string on the host. So this is on the host, and this here is on the container. So those two things are exposed here, and I define here hard-coded some host. So this is where my InfluxDB is hosted on this IP address, and the entry point is this one here. So basically, we start up Telegraph with this, as you see here. Wait for the log file. Otherwise, we would, you would start up. It would take some time until the log file is produced. And what we actually want to is we want to tail the log file. So we have to wait until the log file exists, not to exit with an error here. That's the whole story. Again, this is not Yocto specific. Now, the rest is pretty much standard recipe stuff. So we install certain things on certain places with certain permissions. I described those things here. So there's nothing much to say. This basically just copies files into the deploy directory somewhere. And this is not a package we compose. So we compose a package now out of a tarball and various other files which are going to be installed onto our root file system. Now, another part of this recipe is this one here. So I use systemd, and I create a systemd service which will start up the whole thing. And this is pretty much how you do it. Now, you do not need to do this one here to say explicitly you want to enable it. It's enabled by default. But since I want to switch between enable and disable, I just have this line here as well. All the rest is again pretty much standard systemd service stuff. This now is the unit file I'm installing, so it's basically this stuff here. And again, it's pretty much standard except for the line number 10, which needs some explanation maybe, but I explain it here. So what I'm doing here is I create an InfluxDB name. So this is what I'm doing here. This is a unique name, so it's a shell script which creates a unique name. And then with docker inspect, we check if there's already an OCI Telegraph pre-built container image somewhere. And if it exists, we do nothing. If it doesn't exist, then we do a docker import up container image Telegraph pre-built OCI container and so on as reliable embedded systems OCI Telegraph pre-built. So this was basically my breakthrough here, that it's totally undocumented. I managed to load an OCI container into Docker. So hopefully this is supposed to work also in other Docker versions. At least the one I use now works with this. So maybe they're gonna document it eventually as well. Now, the next thing here is the service. So we start it up. Docker Compose up, Docker Compose down, and so on and so forth. And this is again systemd standard stuff. Nothing much to say about it. Detached mode, so we want to run the containers in the background. Turned out to work well for me. All right, so now we have all this technology in place. So let's now build the whole thing. So with this magic line here, we build now both the application container plus the root file system in a multi-configuration, and we embed it all in the root file system. And if we now start up our board, so what we see here is on the target. Yeah, I'm running it, so you see I'm using 3.1.2 as a current Yocto version. So this is Danfell .2, if you like. I'm logging in here into my target, and I check whether this Docker Compose Telegraph pre-built thing exists somewhere. And you see here some funny boot logs come in here, and you also see at this point here suddenly the service starts up. So a start job for the unit Docker Compose Telegraph pre-built service has begun execution, defined by systemd, and job identifier is this and that. And then basically what it does is it creates some network, it creates a telegraph, and basically what it does here, it starts up as expected the Docker Compose Telegraph pre-built service and finishes. And at this point we're running. So at this point we have now, without a Docker pull from a registry, we managed to start up this service here. Yeah, and if we look into Docker images, so this is basically proof that this thing works, we see that all this was generated 23 seconds ago. If we would pull things from a registry, yeah, the number you would see here would certainly not be 23 seconds, but something much bigger, apparently. Now, we could also inspect a little bit control groups if we wanted to. And I just show you a part of the output of this thing. So you see here that we have here our init process, and we have our Docker service. And in this Docker service, we see here that basically the tail -f is running, and also Telegraph is running. Yeah. So one thing we see here is that our stuff runs as expected. The other thing here, by the way, is also that it makes no difference whether you run this as a container or native. It's all C group stuff, but this is, yeah, for another day a discussion. And yeah, we see here also, if we look into my directory structure, this is basically what ended up at the root file system. So I created the /resi container directory where I usually populate my containers, and you see here are the various files necessary for this thing to work. So we have a Docker Compose YAML file, we have this tarball, which is the initial container image, and then we have here various helper scripts and configurations and wait for file, which we used all over the place here to start up. Well, this is how we could do this stuff. Now let's see what I've done so far and what I plan to look into. So bit-bake recipes for each application technology is known. It might be time consuming depending on which kind of application you want to Yoctoize. OCI containers for each app, yes. Well, once you have the recipe, it's pretty straightforward to do this. Multi-arc technology, I didn't explain this here, but I could also create a multi-arc container image x86 ARM32 ARM64 and push this to the registry, and then if you pull it, the right one is pulled. License compliance, we have an issue with Golang in general, because Golang pulls in dependencies, and then you need to do some special extra steps to check about license compliance. With layered containers, there's another issue with license compliance. I'm not using here layered containers. It's a flat container, which is what I'm using here. So no issue with license compliance here. Up, download to some registry. I have the technology, Scopio, Docker Compose, but we don't need this anymore. We could use it. So what I could do with the example I just showed you is I could now go and upload a new version to the Docker registry, and then I could do a Docker pull and it would pull down the new version from the registry. That's possible. Auto start, again, with what I showed you, you saw it's pretty flexible. So I have the technology for this, systemd and Docker Compose. At the moment, I also saw other companies doing something similar. And once we want to get more distributed, I guess Kubernetes is a good solution. K8s, K3s. Bruce, I'm waiting for the recipes. So yeah, I will need to spend some time on this on both ends. So the team is going to talk about build automation around K8s, I believe, and Tecton. And well, now on the target, it really depends how powerful the target is, whether it should be K8s or K3s. K3s works on ARM and x86, and it's made also for rather small systems. Well, that's it pretty much. Thank you very much for watching this, and in case you want to get in contact with me, here you find my contact information, email and various other pointers, website, LinkedIn, Twitter, Instagram and YouTube. So thank you very much for watching and feel free to get in touch. Hello, ladies and gentlemen.
Thank you, Robert. So if you have any questions, please raise your hands. And Robert, if you could come unmute, that'd be great.
Go ahead, Frank. Frank, you're muted. You should unmute yourself.
Can you hear me, by the way?
Yes, one bad.
Okay.
So while we wait for Frank, Dan, you want to go ahead first?
Yeah, sure. Can you hear me okay?
Yeah.
Yeah.
Okay. Thank you very much for the presentation, Robert. Very well done. I wanted to ask a little bit about the workflow as like, especially interacting with teams that don't use Yocto. When I'm working with others that are on Docker, they're probably really familiar with setting up Docker files and keeping those current with their applications. And I'm just wondering if you have any strategies for kind of synchronizing the work that you need to do between Yocto with work that's happening in a Docker file. Like, it seems to me an ideal way would be if we could import a Docker file into something like this build framework and have it just figure out what it needs to do to build from Yocto instead of Docker.
Okay. So as you saw, what I'm using here is OCI images in order to avoid something like Docker files. But having said that, this is not how I started with all this stuff. So you remember I had one slide where I said I have, if the meta virtualization thing is included, then I use OCI because the OCI functionality is built in meta virtualization. So if not, then I can actually build from the Yocto project a tarball, or let's say a root file system, very similar to what I'm doing here, but not in an OCI format. And this could be imported into a Docker file. But this would mean that the Docker file is just from scratch, include this tarball. So this doesn't really help to synchronize things very much. The problem, if you want to synchronize those things, is that people, if they start working with Docker, they pull in from somewhere some weird stuff. So they cannot tell you what's inside, so you have no way to ever fix license compliance there. So this is a little bit difficult. So I would go the other way. What I'm usually doing is, no matter if I use directly Docker or OCI images, it's very easy to create out of all these also x86 images. So what I usually do is that I can provide for the application programmers things I was generating with the Yocto project, and they can build the stuff on top of it. And they know exactly what's inside, it's already tested, and then it's just a matter of recompiling it ideally, and you can deploy this to the target. Natively in a container doesn't really matter. So this would be my proposed workflow.
Okay, that makes sense. Thank you very much.
You're welcome.
Thanks. Frank is gone. Sean.
Hi, Robert. Thanks again for a nice talk. I've heard your previous talks about the TIC stack in general. Like you were previously mentioning, is there some way in your experience that you are probably the people at Yocto project might see some form of like an SDK being developed for people who are much more acquainted with Docker? As in, like, for example, in traditional Yocto project sense, you can generate an extendable XDK or an SDK so that you can provide it to your application engineers, and then they could just work around with the whole environment that you've already provided, which then in the end makes it easier for porting things on the board or on the target systems.
So this is, I think this exists, all this exists already. So for me, whether it's inside a Docker container, or it's in a QEMU, or it's in a real board root file system, it's pretty much the same thing. It's technicalities. So you just create a standard SDK or an extensible SDK, and you can provide this to your application developers. Now, the trick is that if you provide them, for example, a container, x86 container, they can just pull it with their known workflow. I mean, you build all the stuff with Yocto. You know what's inside. When they want to change, you put the change inside. And then they can actually build on top of this. They can build an application. They can throw the application in. For example, with Docker, you can just mount a volume from your host Linux. You throw in stuff there and you execute it. So I see these, some customers are actually doing something like this, and I find it a quite convenient workflow, especially when we move higher up in the software stack. Think about artificial intelligence, yeah. So if you work with the people who are up there in these high software layers, they have absolutely no idea what's happening underneath. So if you throw at them a Docker container, which they're used to, I mean, they're used to download some weird stuff somewhere from the web, and then they do some apt-get install in there. You throw at them some Yocto container, a Yocto created Docker container, and you let them work on this, and nothing much changes in their workflow. So I think from the SDK's point of view, I don't see any need for new stuff. If I create let's say a Docker image for an x86 64, I just can create, as usually, populate SDK extensible, and SDK with it. And the developer can work with this.
Okay, thank you, Robert.
You're welcome.
Okay, I see Frank has raised his hand. Frank, why don't you unmute?
Hi, Robert. Thank you for the talk. I attempted to use OCI images in an embedded system I worked on, and I really struggled. I mean, ultimately, they're just a tarball, but there's also this metadata that goes along with it. And my problems were generating that metadata. How did you do it? Did you?
It's Yocto. You do nothing. So
Okay.
so think about it. There was one slide where I included two classes. There is one class which comes with Poki, which basically creates for you a tarball, which you could now just import from scratch, import tarball in a Docker file, not OCI. If you want OCI support, you basically just include meta virtualization and you include the OCI support. And meta virtualization now takes care to make out, you have to say I want to create, of course, a OCI image. Yeah. So it's just another image for you. It's, instead of generating a wiki image or a whatever XFS or whatever image or a tarball, it's an OCI image you generate.
Okay, so that layer will generate the accompanying metadata that
yes,
describes the tarball. Okay,
exactly.
Beautiful. Thank you.
Yeah. If you have troubles, just ping me. You have my information. I can help you there.
Okay, are there any more questions? Otherwise, we'll go to our break. Manuel, why don't you go ahead?
Yes, thank you. That might be a very stupid question, and might just have not done my homework, but can you just elaborate a bit on the differences between OCI and Docker? Because I heard about OCI before, but I'm not really, I'm pretty new to this stuff. So if you could just like a few sentences, thank you.
Yeah, so again, there was one slide I passed very quickly where you can find more information about it. Now, in short, there are various container technologies out there, both from the build side and from how the specification should look like and how to execute it, how the runtime looks like and the states and all this stuff. Yeah. OCI is an open container initiative, which basically tries to make a standard around all this. So the idea is that, for example, Docker is an OCI compliant container engine. And so you can actually import OCI containers into Docker as well, maybe also some other technologies out there. That's the main thing. So OCI is something much more generic, and it doesn't only run on Docker, but also on other container runtimes.
Okay, thank you.
You're welcome.
Okay, are there any more questions? Okay, thank you, Robert. Excellent. Thank you, everybody, for the excellent questions. We're now going to go to a break and meet back at 5 minutes after the hour for our talks about Rust. Okay, thank you. Take a break. Okay, we're about to restart. Is Randy here?
I'm here, David.
Okay. Why don't you go ahead?
Let me share my screen. Okay, can you hear me and can you see my screen, David?
Yes, we can.
Great.
I hear an echo
So
too.
my name is Randy McLeod. Oh no. Let's see, if I talk for a while, are you still hearing an echo?
Not from you, just when I speak.
Okay. So my name is Randy McLeod. I work at Wind River Systems on Wind River Linux. And I'm going to tell you about Rust and merging MetaRust into OE core. So overview of the talk is, as I said, to talk about Rust and the MetaRust layer and the work of merging it into OE core and why we want to do that. And then once we actually get there, what'll come next. So I'm assuming that people don't know much about Rust or MetaRust. So this is a very quick talk. So I don't have, it will be a full language tutorial or things like that. It's very much an overview. So Rust is a memory safe and concurrency safe, performance oriented systems language, much like C or C++. It doesn't have a garbage collector or things like that. So it's suitable for implementing operating systems or performance critical deterministic software. And it goes back a while, started in around 2006, as I mentioned on the slides. It was adopted by the Mozilla Foundation in 2010, and they had a 1.0 release, which guaranteed backwards compatibility back in 2015. So it's, in the language world, it's probably a little newer than Go, but same generation. For several years now, it's been a very popular language and winning the Stack Overflow annual survey of developers' favorite languages because of the properties that it advocates and tries to deliver to developers. So the idea is performance, control over memory safety, and fearless concurrency, and a really good community. There's been several Rust conferences over the years, and portability as well is achievable and fairly easy, but of course you can write platform-specific code as well. So I mentioned the performance. I haven't looked at the language shootout website, that it's similar to C and C++. The memory safety is the default. You can write memory safe code in C++ if you're very disciplined, and many people achieve that, but people are fallible, and by default, Rust is safe. Rust will let you write unsafe code if you use the unsafe keyword, and even in that case, the compiler will insist on certain workflows so that it doesn't give you complete freedom. Whereas in C and C++, you're free to shoot yourself in the foot, as they say. So because of this memory safety and the type checking and the language design, many concurrency errors are also caught at compile time. And so the cost of this memory safety and concurrency freedom is slightly longer compile times, which I see as being a replacement for running the compiler and running Valgrind and running other tools that come along with the C and C++ environments. Rust isn't just a compiler, it's also a collection of tools and a community. So Cargo is the build tool. They try to have very clear docs and helpful error messages, which is similar to the GCC versus Clang advocacy. So let's start with a simple program when you're compiling manually. To get started on your workstation, Ubuntu or Debian or Fedora, whatever you like to use. You can either use the system package manager these days, I think, but most people, especially when we got started a few years ago, use this horrible script to install from the web. So you can look at the rustup.rs website and follow their directions. Once you've done that and you log back in again, you can type in a hello Rust file and then just invoke Rust in a very much analogous way to using GCC or Clang. And when you look at that output of the compilation, you'll see that you depend on the 4 shared libraries that I list there. This shows you that even though it's a simple program, Rust has these 4 dependencies. So it's prepared for multi-threading, it's a libp thread, and it has libc, libdl, and libgcc. The size by default is fairly big, about 280K, but it's with a bit of work and some options, you can strip it down to 6K. So it's clearly similar to C and suitable for embedded systems. So as you scale up to larger and larger projects, you'll see that Rust is statically linked, and I'll probably talk about that in a future slide. The more normal way to use Rust is to use the cargo package manager. And so you'll start with the cargo new to create a new project. And you can either create a binary or a library. The default is a binary, so create a hello cargo project and cd into that directory, and you'll find that you've already got a very stubbed main created for you. So then you can just type cargo build, and that'll generate your binary. You run cargo run to run the binary. Cargo test, so the development environment is set up for industrial software approaches. So tests are integrated into the language and into the package manager tool. You can also do, Cargo also knows about a repository for packages on the web called cargo.io. And so you can use the command line tool to search for something like Tipsy, which is a network protocol that I worked on 10 years ago. It's fairly obscure. So I searched for that the other week, and surprise, surprise, someone has written bindings for the Tipsy network stack in Rust. And that sort of gives you an indication of the scale of the development community and how many packages are available. I think there are roughly 50,000 packages. So, it's not small, but it isn't sort of the millions that you see for software on GitHub in every language imaginable. So you, let's say you assume you don't want to install Tipsy. Let's look at a developer tool. So you can run cargo install ripgrep, and I'm just going to walk you through what that does. Ripgrep is a faster implementation of grep written in Rust. You can also read it as rest in peace grep, because there's no longer a need to use grep, perhaps. So the first thing on the second line here is that it updates your cargo.io index, and then it downloads the main ripgrep program and all of its dependencies, which in this case are 14 crates. A crate is essentially a library in the C and C+ world. And then it compiles everything in the order required, so it handles the dependencies, much like bit-big recipes do. And then tells you that it's finished and installs it in your home directory, which is in your path by default. And then you can run ripgrep or RG, and you'll get slightly better performance and slightly different usability than grep, but it's a nice tool. So that's fine. You might say, well, why does Yocto need Rust? And the bottom line is that the more and more software is being implemented in the language, so it's time to merge it into OE core. There'll be pros and cons, of course. We've already suffered from not having Rust because several packages, specifically librcg, have been held back a few versions because we don't have the toolchain in OE core. So I mentioned the other 2 points, the pros of using Rust. the cost will be, there'll be another tool chain to support, and we'll have to develop the expertise, and myself and some of my coworkers at Windover are going to be able to do some of that, but of course we'll need community to pitch in as well. I've mentioned the downsides, the Rust build times. I don't have actual numbers, but there can be like a factor of 2 or 3 longer build times than C or C++ application of similar scale. But as I mentioned, this is the cost of safety. The compiler is doing lots of checking, is also doing static linking by default. So if you have 2 Rust applications and they share all of their libraries, the 2 applications will duplicate the text code instructions for each of the libraries, unlike having shared libraries in C and C++. This is, it's possible to avoid that in Rust, but it's not all that common. So one solution to that people have used for a replacement for core utils is much like BusyBox produces a single executable and produces a series of links to that. You can take the same approach. And I think I was one of the people who started on the Meta Rust layer did the same thing in their application at Lexmark, a printer company that has been using Rust now for a few years. So we don't want to just run cargo Rust code on our personal workstations or work workstations. We want to do cross-compilation and embedded systems development. One way to do that using Rust, because to do this statically linked, is to just install the GCC cross tool. So I'm doing this on Ubuntu. So I install the AArch64 toolchain, and then I add that as a target in using the Rust up tool. And if I modify my cargo config to specify for the AArch64 target, I'm going to use the linker given, then I can just call cargo and say build for this AArch64 target, and it'll happily cross-compile. So cargo and Rust specifically, because they're based on LLVM, already have the ability to generate code for a variety of targets. And so this is fine. It's very convenient for developers, I think. You just build on your own workstation, you produce a Arch64 target binary, you copy it over to your system, and you can run it. But of course, if you're doing production environment, you want to be guaranteed that the exact versions of both Rust and your linker and your C library and so on all match up. So we probably want to teach cargo how to do that by using the Yocto SDK C and C++ tool chains, or just put cargo and Rust C in our SDK. And that's something that I haven't done yet. I'm not aware of anyone who has. So let me know if you know more about that. What is the Meta Rust layer? It's a Yocto compatible layer, as you might expect. It produces the Rust C and the cargo cross tools. It was started about 6 years ago by the people I list here. So there's about 35 people who have contributed to Rust C. I'm not one of them, so I'm really just trying to move things over to OE core. It was more active in the early days with several hundred commits a year, but recently it's more like 40 commits a year. And the major activity is keeping up with the Rust community. Unlike a lot of toolchain development cycles that are sort of an annual or or less frequent up-rev cycle, Rust releases a new version every 6 weeks, and it does have longer-term sort of long-term support milestones. I think they call them additions. So we need to come up with a strategy about maybe supporting the 2018 edition, I think it's called, or optionally using the bleeding edge latest official release. So if you look at the what's in the MetaRust layer, it's a typical stage 1, stage 2 toolchain build and a sample Hello Rust application. And if you look at use the PY boot chart task to what I did, I believe was I built core image minimal, and then I just added the Rust Hello World application. And of course, that needs to build the toolchain. And so you can see if you squint really hard, you can see the different stages of the build. And I have the full PY chart. This is the summary, of course. The take-home message in this slide is that this is building Rust native, and it is really quite slow. It takes, I think it's roughly 10 minutes on a fairly hefty 192 core build system that I have at hand. And anyway, so it works, and then end up producing the Hello Rust and adding it to core image minimal. So we'll want to fix that CP bottleneck, but we just haven't gotten there yet. So you have this wealth of BitBake recipes on crates.io, as well as other things that are not necessarily published to the community, but you can find on GitHub, or you have within your on your file system is your own project or your work Rust project. And so there's a tool written called Cargo BitBake. It's on GitHub, and so if you it's also on the crates.io website. You can just use Cargo on your workstation to install Cargo BitBake. And then you go to, say, for example, the ripgrep source repo that you've cloned from GitHub, and you type Cargo BitBake, and it'll produce a BitBake recipe. And the contents of the recipe include everything you need to be able to compile it using MetaRust. And so the end result is you can get BitBake ripgrep and install it into your image. So that's fine. That works in MetaRust, and so now we need to move things over. It shouldn't be a big deal, but you never know. I've been sort of working on this off and on for probably far too long, but moving things over from one layer to another is fairly easy. I've done that. You add a couple of recipes that depend that Rust needs and move them over from Meta OE. That's also fairly easy. And then try upgrading librSVG to, I think, the 2.5 branch. And librSVG is a GNOME project, and GNOME has really started switching over to Rust, but they also need to deal with backwards compatibility. So librSVG, which is used to be written in C, has a C API, but the developers are trying to maintain that API, but provide the core functionality of the code in Rust. And so I'm not sure if this is done yet. I have something that builds, but I haven't linked applications against it, so I suspect that there is still a problem. There are two ways that librSVG can be built. One is using AutoTools, and one is using Cargo. So currently the Cargo approach works, and the AutoTools doesn't. The bottom line in the AutoTools build is that you try to get the part of the build asks rustc to print its configuration, for example, and it just can't find the configuration. So it looks to me like it's a configuration issue, because the stage 1 and stage 2 versions of the compiler are fine. And I started debugging that, but I haven't resolved the problem yet. So I'd also like to thank Adrian Bunk for this Cargo disabled BitBake vendoring, which enables the Cargo build to work. So I went on after that and tried to look at what else needs to be done. And GStreamer and probably other OE core packages depend on librSVG. I also did a BitBake world, and there are a few problems with that as well, including the fact that for some reason, I can't exclude Rust, C, and cargo from the target build. So that's probably a trivial thing, but that's where things are at the moment. And the reason I wanted to exclude them is that that's one of the limitations of the MetaRust code, is that you cannot build cargo in Rust C for the target yet. So I'm almost done. I haven't heard anything. I hope that things are in good shape here. Let me continue. There's another problem with the current state is that RISC-64 isn't supported in the version of LLVM that we have. There is an update of LLVM to 11, and it's possible that this will be fixed. So we'll need to bring that into OE Core, hopefully in the next few weeks. We also need to be able to support building Yocto and OE Core on ARM64 build systems, and that may be possible. I just haven't tested it yet. RustUp does work on my Raspberry Pi 64-bit Raspbian distro, so it's possible. It looks like it shouldn't be a problem, but we'll have to see. So I've mentioned the other 2 points, so I'll skip over those. And so what's next? The plan, as usual, is to get it merged, do something else, and then profit. So we'll see how that goes. We'll need to continue to track the Rust upstream 6-week release cadence. Currently, we have Rust has its own copy of LLVM. There's not a huge difference, but it's not a trivial difference either. So we need to try to unify those 2 repos because they're fairly large, and it's not really a great idea in terms of software footprint to have these duplicates. It'd be nice to get the Rust cargo environment cross-compiling to build on the target. I don't think that's necessary for merging, but we'll have to wait and see what people think. And dynamic linking would also be nice, but again, that's sort of a longer-term requirement, I think. There has been discussion in the Linux community environment about doing driver development in Rust, taking advantage of its safe nature. And I don't think there's any plan for that. If anyone knows, I expect that'll be a year or 2 down the road, so it won't affect the spring release of the Yocto. So if anyone knows more about that, please let me know. And I'm sure there are many other things that I don't know about, so I welcome input and anyone's ideas about what else we would need to do. So thank you for your time, and I open for questions.
Very good. Okay, to ask a question, go to the participants and raise your hand.
So I'll ask a question of the audience. Has anyone been using MetaRust, and what are your experiences with it in a production environment?
Someone asked in the comments if have there been any experiments with dynamic linking?
Certainly in the Rust community as a whole, but not in a Yocto that I'm aware of. Actually, no, that's not true. The guys from Lexmark have this sort of mono application design, and they make basically a shared object for the bulk of their mono application, and they have a simple wrapper for the binary. I've forgotten why that's useful to them, but you know, that at least exists and works.
Someone raised their hand. Want to ask a question? Mel Shawi.
Yes. Thanks, Randy, for the presentation. I would like to ask you about the Rust compiler build and why it's so slow. I think Rust is something pretty modern, and what I expect is the building process started with, or the development started with multi-threading in mind. So what is the blocker here, or what is the exact issue to build it more quickly?
Randy, I muted you because there is some echo otherwise, so you have to unmute.
There we go. That explains why I wasn't able to interrupt. That's good. So the answer is I don't know yet. I've been focusing on trying to get everything working. And once you've built the compiler, of course, you don't need to rebuild it. So it hasn't been sort of a major blocker for me. So it could be something very trivial. I have seen commits in Rust that do try to use the right Yocto variables to control number of jobs and number of the parallelization of the build. So I just haven't taken the time to look yet.
Okay, thank you.
So since maybe gives people a minute or so to think about other questions, I'll sort of do my backup slide or emergency slide. One of the things I've been mulling over but haven't really started working on yet is bootstrapping tool chains. So there's a project on GitHub called Bootstrap that bootstraps Rust from well, let's start from the beginning. Right now, we require a tool chain on a host to build anything in Yocto. And so it'd be nice from a purity point of view to not require that large binary, you'd be able to bootstrap the tool chain itself. So there's a GNU project called Mass, which starts with a 5,000 line of code C program, which is written in C that generates the Mass CC compiler. And from that, you can bootstrap yourself up to tiny CC and then glibc bin utils and GCC of these particular versions. And from there, you can bootstrap the rest of the world. You could do a similar thing with Rust. Rust was originally written in another language like OCaml, perhaps, but the early versions of the Rust compiler were written in C++, unlike the current version, which is written in Rust. So in theory, you could take this mrust-c compiler, which is written in C++, and bootstrap the 1.2.9 version of Rust, and then follow a series of 6 or 8 steps to get up to the current version. Of course, this would be horribly slow, and you would not want to do it very often, but it would be a nice thing to do from provability, reliability, and trust, which some people worry about. Not one that I don't have any customers who are interested in this, but it's an interesting idea, I think. Any other questions? Okay, why don't we go on to the next talk? Paul Barker is going to have a little bit of overlap with me, but he'll talk more about Rust as well. David?
So technically, the next talk starts. Could you mute, Randy? Thank you. The next talk starts at 45 minutes after the hour, which is in 10 minutes. We can just take a brief break and then start Paul on time for people who are joining for his talk.
Nico, do you want to just test the first 10 seconds of my video, make sure the audio comes through the Zoom all right?
That was exactly what I was about to do. Just looking for.
I am ready to jump in and do the demo live if I need to, but it worked well on the recording, so it'd be nice if we can use that. Hi folks, this is a recording of my presentation for the Yocto project Virtual Summit Europe, scheduled for October the 29th, 2020. Yep, that sounds perfect to me.
Okay, good. So
You close the download bar at the bottom of your browser window. Should be even better. Cool.
So Nico, shall we start at 45 minutes after the hour, or do you want to start early?
no, we should start at 45, just because we said we would try to stick to the schedule, so we should.
Okay, very good.
Everybody's here, so if anyone has any question on anything, you could also use the next 5-10 minutes to just chat about the project. So feel free. I mean, if you want to say or share anything, we can use the time like that as well. I mean, I'm not forcing anyone, but if there is anything to say, that's also good.
Is Randy still here?
I am.
On the Rust compiler, I would imagine that we have a lot of problems because they release so often, as you were saying. Do you think it would be possible to include like a fairly recent version in like the build tools tarball, and that would help with some of that? Like, then you don't necessarily have to build Rust inside of you've got a known version of Rust that you can build with, right? As kind of a host tool.
Yeah, I suppose you could do that. You do need a bootstrap version as well, so that's a binary that you have to download to get started.
Right.
Because the compiler is written in Rust. So, you know, I suppose conceptually that could be used, but and maybe even as the default. And if the user wanted to have the new version, they could. So I'm a little surprised. It's a group of 100 people or so. No one is using Rust yet. Do people have plans? Or I know I've heard from some of our Wind River customers, and they're certainly interested in Rust. So what are people's ideas?
So I'm definitely expecting to be using Rust a little more. Be nice to collect some recipes for things like ripgrep and other tools. Because at the minute the meta Rust layer is a little sparse beyond the toolchain itself.
Yeah, I agree. And so I was thinking about that as well, obviously, and we could even have a meta cargo IO and basically mass translate the latest versions of recipes on a regular basis.
The question I'd have as well is the cargo bitbake tool, which I'm demoing in my presentation, is written in Rust itself, whereas most of our Yocto project tools are written in Python. So there's kind of an open question of should we rewrite that in Python for maintainability. I need to see if there are Python bindings to the cargo library.
I suppose if you want to do that, it's a reasonable idea. The alternative would be to add the the recipe to the OE core itself, or if we're going in that direction, I really don't see the need to translate it to Python.
I'll follow it up with you later, because there's not really the time now. But yeah, there are some pros to moving it over to Python. Yeah, we can chat about that later, I'm sure. Yeah, in advance my talk starting, it's pretty much 34 minutes, so it'll take the full time slot. So if anyone has any questions, I'll answer them in Slack and or Zoom chat as we go and afterwards.
Okay, we're 1 minute to the next presentation. Thank you, Randy.
Next time, I won't leave as much time for questions, David.
Okay, it is 45 minutes after the hour. Why don't we go ahead and get started?
Hi folks, this is a recording of my presentation for the Yocto project, Virtual Summit Europe, scheduled for October the 29th, 2020. I'm going to be giving you a demo of using Rust with Yocto project. So Randy will have given a talk, more of a presentation style about this. I'm going to have a couple of slides, and then I'm mostly going to spend my time on a demo for you, showing you how to actually use some of this stuff in practice. So first of all, a little bit about me. I've been involved with the Yocto project since around the middle of 2013, and since then I've worked across the embedded stack, bootloader, kernel, Yocto project, and various other components along the way. These days I am working as a principal engineer at Consulco Group. We provide basically any sort of consulting around embedded Linux that you may require. We've got a lot of experience in all the areas I mentioned before. So some personal contact details if you want to follow up about any of this. I've got my email address there. I also have a personal website and a Twitter account. Feel free to follow up using any of those methods. So this talk, I'm going to give a brief introduction, and I'm going to keep it brief because most of the discussion about Rust is going to have been covered by Randy already. I'm then going to show a couple of details about the interaction between the Rust language support in Yocto project and our license compliance features. I'm going to show a couple of slides about how to actually get Rust installed on your development machine and why you might want to do that, and then I'm going to move into the demo. So diving straight over to license compliance. Like many newer programming languages, Rust has got its own package manager and build tool. And for Rust, this tool is called Cargo. So this is similar to Node.js ecosystem built on top of JavaScript that's got the npm Node package manager, and similar to the way Go has its own build tool as well. Now these tools often present issues for us in the embedded Linux world. The sorts of things we care about just don't seem to be first-class concerns sometimes to the developers of these tools. So, you know, all the things we've put in place to handle, you know, what we need when cross-compiling, what we need when building for a customized image to go on a target, and what we need to achieve license compliance. Those features sometimes aren't there. So what I did, I took a look at this and I made a list of all the features that, in my opinion, we need in order to, you know, be able to properly support working with one of these language package managers. And these are features that the language package manager itself needs to provide so that we can integrate with it well from Yocto project. So we need the ability to build offline. In Yocto we have a do fetch stage that's separate from the do compile stage where we actually build the software, and we want to make sure that separation is clean and we don't end up with additional elements being fetched during the do compile cycle. We want to be able to download sources in some sort of archival form, rather than just some kind of online build system. We need something that we can archive, keep long term, come back to years later, or provide to our customers as part of our license compliance. We need to be able to capture the license text and other collateral that goes with a project. So this may be, again, part of our license compliance activities. It may be scripts that are needed to rebuild the software, other things like that. We need to be able to capture these files as well. We need whatever tool the package manager uses to download sources to support HTTP or HTTPS proxies. That's something we support in the Yocto project. And lastly, we need to be able to set up our own source mirror which may be locally on the machine we're working on, or maybe some sort of internal server within a company, that we should be able to set that up and use that as the source for our downloads rather than going to some sort of official upstream all the time. That should be configurable. So looking at Rust in particular, Cargo, which is the build tool used by Rust, actually integrates really quite well, and all the features that I described in the previous slide that we need are supported by the way that Cargo is integrated into the Yocto project within the Meta Rust layer. The one limitation that I've found is that, you know, if you've got a project and it has some additional dependencies, the license and the license text will be captured for the project itself, but they will not be collected for all the dependencies of your project. So that is something that needs a bit of extra work, and at the minute I would say just be careful. Make sure that you're manually capturing that information for any of the dependencies that your Rust-based projects have when you're building them with Yocto project. So that's pretty much all I have on license compliance fairly briefly. The next thing I want to run through before I move over to my demo is just how to install Rust on your development machine. So installing Rust natively on the development machine is not a requirement of being able to build recipes which use Rust within Yocto project. But it is required if you want to run the Cargo Bitbake tool, which I'll be demonstrating, which is used to auto-generate a recipe for a project written in Rust, and being able to build and run software natively can really help with debugging. So those two are kind of my reasons why I think it's important to install the Rust toolchain natively on your development machine. So the canonical way of installing Rust is to go to the rustup.rs website, and that will give you a couple of options. The straightforward way on a Linux system is this curl through shell pipeline here that just downloads the latest version of the setup script and runs that. It will ask you where you want to install Rust. It will set up the environment variables on the next login, but if you want to go straight ahead and use Cargo and Rust after you've installed them in the same terminal, you will need to source the environment file that is created. And if you want to use the Cargo Bitbake tool, once you have Rust and Cargo installed, you can then run this Cargo install command at the bottom that will go and download the source for Cargo Bitbake and build it. So those are kind of the prerequisites if you wanted to repeat what I've done in the demo. So yeah, there are a couple of tricks I'm just going to point out about my demo. These are just things to make it flow smoothly on the day. So I've got pre-populated shared state cache. That means things are going to build very quickly. Don't expect them to build that quickly on your system. Things do. Rust toolchain itself, built within Yocto project, does take a little while to build. But yeah, for the purposes of getting a demo within the sort of 20-25 minutes that I'm going to have, yeah, pre-populated shared state cache is critical. I've also got local mirrors of the layers I'm using of Pocky, Meta Open Embedded, and Meta Rust. That's going to save time in my git clone step, and is just a lazy way of making sure I get the same commits that I tested. And I'm running on Arch Linux on my build machine at the minute. Arch Linux isn't really a stable base for Yocto project builds, so I'm using Podman and the crops containers to run my builds on a stable distro. And all those things will become apparent as we go through my demo. I just wanted to kind of flag those things up front in case you want to replicate what I'm doing. So I'm gonna pause for a minute here and then come back with my demo. So this is going to be the demo section of my presentation. I've got a Visual Studio Code window open, and this is connected to my Linux build machine. I'm actually running Windows on the desktop here for various reasons, but yeah, using the remote over SSH capability of Visual Studio Code, I can work pretty well. So the first thing I'm going to need is a terminal. Should surprise no one. And I have a project directory. So I'm going to make myself a new directory to work in, which is going to be called YP Summit 2020. And what I'm going to do is I'm going to reload my Visual Studio Code instance in this directory. So this just gives me a nice setup for using Visual Studio Code because I've set the root directory of my project. Right now it's looking pretty bare, so let's start bringing some things in. So the first thing we're going to need in order to demonstrate something with the Yocto project is our core layers themselves. So I have a mirror of the Pocky repository on my machine, as I mentioned earlier. I'm going to clone that, and I'm going to pick up the Dunfell branch. So this is pulled Pocky in here. I'm also going to pull in the Dunfell branch of Meta Open Embedded, as that's going to be a dependency of the Meta Rust layer. And I'm going to pull in Meta Rust itself, but Meta Rust does not have a Dunfell layer. Dunfell branch. Meta Rust doesn't have a Dunfell branch, so we're just going to pull in the master branch of that. So this gives us our 3 layers that we're going to be using today. And with these layers and a little bit of additional work, we should be able to show some Rust code being built with the Yocto project. So let's take a little step further. So looking in Pocky, one thing I'm going to want is the ability to build, run Yocto project builds. As I mentioned, I'm using Arch Linux on here, so I actually want to be running my builds within a container. So I'm using Podman as a container manager, and this is going to be the command to start my container. So I am running a container, I'm using -rm to remove it when I'm finished, I'm using -it to make it interactive and give it a terminal, and then I'm using -v to mount some volumes. I'm mounting the current working directory to /w, and I'm mounting this cache directory, which has my downloads directory and my state cache, to /cache within the container. And I'm using the Debian 10 crops container. So if I run this command, I should be dropped at a prompt in what looks like a Debian instance, which is good. So I think I'm in slightly the wrong place. I am going to redo that from the top levels so that I can see the other directories I've created. So let's have a look in Pocky. So the first step, like we would with following the Yocto project quick start, is we're going to set up a build environment. This is pretty much an out-of-the-box Pocky setup. We're then going to add in the layers that we want to use. So we're going to use the bitbake layers tool. This has a couple of useful commands. The ones I'm going to be using are add layer and create layer. So I'm going to use the add layer command. to pull in a layer. So you give it a path to a layer directory, and it's going to modify your BB layers configuration for you, as well as just checking running a few sanity checks to make sure everything's happy. So I'm going to do that again to add the Rust layer into my build. And the last thing I'm going to do here for now is use bitbake layers create layer. So I'm going to be putting together some recipes for software that's written in Rust, and I'm going to want somewhere to store them. There's a few different ways of doing this. I'm going to create a layer from the start and just drop the files straight into the layer. So I'm going to create a layer 2 levels up, and this is going to be just called Meta YP Summit. So this has created a Meta YP Summit directory here on my system with conf file and some example recipes. It's also printed a message saying we can add our new layer with this bitbake layers command. So I'm going to pick that up and run that. So yeah, we've now got all the layers that we want added, and just to confirm what that looks like, let's move our terminal down out of the way. And yeah, we've got a few changes have been automatically made to our BB layers conf file to include these various layers. And to check that this is happy, we're going to build core image minimal. And this is just going to take a second to parse all the recipes in all these different layers. And then it's going to run a build, which hopefully, well, I've made a mistake. I realised straight away that I had made a mistake. This is the joys of doing a live demo. And of course, I've run into a bit of a lockup here, which is not great at all. So what I'm going to do is I'm going to copy over my site configuration file. So within /cache I have a site.conf file. I'm going to bring that in, and this is just a simple file that says where to find my shared state caches, which are split by distro and version, and where to find my downloads directory. So with this in place, my build should run properly now. So this should actually be able to find my shared state cache mirror. So it's going to reparse everything. And yes, it's picking everything up from my shared state cache. So at this stage, I've added some additional layers in, as I say, but I've not really done anything with Rust itself. I'm just doing a bit of a sanity check to make sure that a simple build succeeds. And this really doesn't take very long at all, since everything is populated in the shared state cache. So now we're in a pretty good place, and we're going to also just quickly try out run QEMU. Since I'm in just a terminal here, I'm going to use no graphic, and since I'm in a container and I've not got access to some of the device nodes I might need for network tap, I'm going to use Slurp, which is the option for software networking. And this is going to boot my image that I've just built. and we can log into this. Now I'm just going to demonstrate two commands are absent. So there's a hello isn't found and print-rand isn't found. So these are the two utilities written in Rust that I will be implementing and adding to the image. So I just wanted to show, these are not in the base image when we start off. We can close down this image and we can start thinking about doing some things in Rust. So what we're going to need is a new terminal. So this terminal is inside our container that we're using for building. We're going to need something that is outside and is in my host system, because what I have in my host system is the cargo tool, which is the build and package management tool for Rust. Now cargo has some pretty useful commands. So one of those is cargo init, which is going to create me a new package. I'm going to create a package called hello-temp. It's temp because I'm going to be replacing it with a pre-built hello package in a couple of minutes. But for now I just want to show you what you get from cargo init. So it's going to create me a directory and populate it with a couple of files. It populates with a git ignore to ignore the target directory that is created when you build a thing in Rust, and it's going to populate a cargo.toml file. So this is the configuration file for cargo, contains the project metadata, and it's going to give us a source file, and this is what hello world looks like in Rust. It's pretty straightforward. It looks kind of similar to C if you squint hard enough. We've got a main function and we're using the printline macro to print the hello world string. And I'm just going to show you with this, if we cd into this directory, we can use cargo build to build the project in the current directory. And that builds fairly quick when it's just building a hello world program. And we can use cargo run just as a shortcut to run the binary that's been produced. And we see that this prints the string hello world. So I'm going to briefly pause there. So let's move on to the next step of my demo. We've got some code written in Rust. Let's look at how we bring that into Yocto project and build it within our environment. Now the first thing that we need is this to be somewhere online that we can actually fetch. So this is why I've created a hello-temp. What I'm going to do instead is git clone a thing I made earlier. So up on gitlab.com under my user I have a Rust hello application. This is similar to the hello I already did, but with just a couple of changes. So I added a license file, I added a readme file, and I added a couple of lines to the project metadata. I added the license entry, I gave it a description, and I added a line pointing at the repository. So this is kind of what you'd expect a project to look like once it's been published somewhere. So if we step into this hello directory, we can use the cargo bitbake command that I discussed earlier to generate a bitbake recipe, and that drops a bitbake recipe in the current directory, and it looks fairly similar to a sort of bitbake recipe you'd see, but with a couple of differences because it's auto-generated. It's kind of based on a very verbose template. But yeah, we're going to use this cargo BB class that's going to contain all the instructions for building this with cargo. It sets the source URI pointing at the remote of my git clone that I made. It says source ref to the revision that I have checked out. Sets the S directory, a couple of other little bits. There's an empty addition to the source URI here, which will make more sense later. It's found our license file, captured the MD5 for some of this. It's put the description that I gave in my cargo.toml file into the summary in the recipe. It's put the repository entry into the home page, and it's picked up the license entry. And the bottom of this file has a couple of include statements. These let you add additional lines to either of these style of .inc files in case you regenerate this recipe in the future for, say, an updated version of the software. You want your customizations to be in a file that isn't going to be regenerated. So we've got a recipe. Let's put it in a layer. So we created this meta YP summit layer to store our recipes in. So we're going to have recipes YP summit, and we're going to have a Rust folder, and we're going to move our hello recipe in here. Now this is nice as a simple recipe, but it's not got any dependencies. This is just very, very simple. So what we want to do is we want another project as well. That's just a single step more complicated. And we're just going to pull this one straight down from GitLab. Again, from my GitLab account, we have print rand. And this just prints a random number. It's really that simple. Print rand, looking at, again, it has license, has a README, has a cargo toml file, and it has some source written in Rust. We look at the cargo toml file first. The main difference here is that we have a dependency listed. We're using the rand crate, and we're specifying version 0.7 because this is not yet at a 1.0 version and the API might change. We're going to pin the version somewhat. Yeah, the rest of this looks pretty much as the other project configuration file did. The change in the source code itself, we're going to use this use statement to pull in parts of the rand crate that we need. We're just going to generate a random number by calling the random function, and then we're going to use the print line macro to print that number. So let's just take a look at that before we move on. So in our print rand directory, if we run cargo build, this is where it's going to be a little more interesting because it's going to build some dependencies. So you see it compiling the dependency crates, and then you see it compiling print rand itself. And then if we do cargo run, it's going to generate and print a random number that's going to be different every time we run it. So let's generate a recipe for this using cargo bitbake. And again, we have a recipe file that's been generated. This fairly similar to the previous one. The main difference is these source URI entries. So this is using the crate fetcher that gets added into bitbake in order to pull down the crates. We have not just the rand crate that we listed as a dependency, but we have all these other bits and pieces that are dependencies of that crate. So it's going to pull all of those down and use them to build our software. The rest of this looks the same as our Hello World recipe looked. So again, we're going to grab this, we're going to put it in our Rust directory within recipes YP Summit within our layer so that bitbake can find it. Now if we hop back over to this terminal, which is in our build environment, we can build both of these. We're going to build them both at once just to save some time. and this is going to pick things up from cache because I built them previously. But obviously, if you do this, it will take a little bit longer on your machine. It will first build the Rust toolchain from source, and then it will build the recipes that we listed. So that's looking pretty good. Things were successful. We're now going to want to test these things out. So we're going to want to add them into an image. So we're going to create ourselves a little image recipe just so that we can test this out. So we're going to create a folder for our images, and we're going to create a new file that is going to be YP Sonnet image. We are going to pull in recipes core images core image minimal. Require is like include, but it throws an error if the file is missing. Obviously we expect this file to be there, so that's, we want to catch that error if it ever is missing for some reason. We then want to add our recipes to image installs. We have a hello world and we have a print rand. So this is a simple image recipe. Let's come back to our terminal and bitbake our new image. Hopefully this will work. Let's see if I type that out correctly. So again, it's pulling things from the S-state cache. And it's building an image. So that's pretty good progress. So yeah, this image is going to be like core image minimal, but it's going to have these two additional utilities that are implemented in Rust added into the image. So the last thing we're going to do is we're going to use run QEMU, and this will pick up the latest image that was built, which is going to be our YP Summit image. And hopefully this is going to have our utilities in it. So if we take a look, we log in, we have hello, which prints hello world, and we have print rand, which prints a random number that's different each time we run it. So we have successfully implemented some simple applications in Rust, one of which, hello, had no dependencies, one of which, print rand, had some dependencies. We've generated recipes for both of those elements using Cargo Bitbake. We have added them into an image recipe. We've built everything and we've tested out under QEMU. So yeah, that concludes everything which I wanted to demonstrate. So thank you very much for your time. I'm happy to answer any questions afterwards by probably discussion on Slack at this stage. So thanks very much for your time, folks.
Thank you, Paul. So if you have any questions, please raise your hand. Paul, you made some comments in this chat session about stuff that you're going to be looking at around the crate fetcher, perhaps? You could address that.
Yeah, so discussions I've had with Randy about bringing the Meta Rust layer and the Rust support into OE core. There's kind of two parts to it. One part is the recipes and classes that will go into OE core, but there's a fetcher for those crate URLs that we saw being added to source URI. So that fetcher kind of gets monkey patched into Bitbake at runtime from the Meta Rust layer at the minute. We're going to want to move that fetcher into Bitbake itself, submit it to Bitbake. Yeah, one thing Jan brought up there was that there doesn't seem to be any validation of the crates that are downloaded. So for each of those crates, it's downloading a tarball of source. So yeah, what we would want is somewhere to check the hashes for those. So yeah, that's something I actually hadn't thought about before. We'll definitely be taking a look at that.
Okay, there's a question in the chat session. Is Rust available for other arches, ARM, ARM64, PPC64?
I believe it supports most of our target architectures. Certainly you can build things for ARM with Rust, I think. Randy was saying it doesn't support RISC-V in 64-bit mode at the minute, only 32-bit mode for RISC-V. But yeah, I'm not sure about PPC64. That might be something we want to check out.
Very good. Sean, why don't you go ahead and unmute?
Thanks a lot, Paul, for the presentation. I'm just curious about the language in general. So by profession, I'm much more into research, and we need to build up really quick prototypes on embedded systems in order to just get that state-of-the-art check or whatever that we are required to. The question is, does Rust actually have like decent, as you call it, quote unquote crates for basic interfaces like I2C, SPI, and all that kind of things, or is that something that the community is still building upon?
So I don't know the exact status. What I will point you to is the Rust embedded working group. If you search for Rust embedded WG or working group, you'll find that they're for their working group, and that's the embedded devices working group. They're a team of people working on Rust support for embedded devices. Some of that's embedded Linux, but some of that's also like even lower level stuff, support for Cortex-M, architectures, RTOSes, various things. There is, I can see some projects for I2C devices and SPI devices. So yeah, take a look at that. The story for embedded in Rust has changed massively over the last 2 or 3 years. When I first looked at Rust about 2016, early 2017, I didn't feel it was there yet, but looking at it again now, I think, yeah, the story for embedded is very, very good.
And doing a cargo search for I2C brings back actually almost 200 crates. So looks like there's lots of I2C work that has been done.
All right, sounds fantastic, guys. Thanks a lot.
We have 2 more minutes for questions. So I enjoyed your seeing your development environment as much as I enjoyed your presentation, Paul.
Yeah, I did try to subtly sneak in a demo of using Visual Studio Code and using building in containers as well as Rust.
And your site file, do people do that?
I can't remember where I got the idea from, but yes, it's Bitbait will pass a site.conf file as well as a local.conf file. And it's a common place to use to specify where you've got download directories, shared state caches and things like that. I just have a few tricks to allow me to separate different shared state caches for different distros and versions and projects. I should share that online somewhere after the conference.
That sounds like a best practice. Okay, we have about 30 seconds. Any final questions for Paul? Paul, thank you so much. Okay, let's go on to our next presentation. Kim, take it away.
All right, thanks, David. Can you hear me well?
Yes.
Okay, and so I'm gonna just project. Can you see my presentations?
Not yet.
Yes.
There we go.
All right. Okay. So okay. So do you see the full screen now?
Yes.
Yes, I do.
Thank you. All right. Thanks, everyone. So today we're going to talk about size optimizations, some techniques to apply for size reduction, and roughly I will go over what you can do within Yocto framework um, to reduce size of your firmware. What tools are available that you could deploy to help yourself. And then I'll also talk about some of compiler tools and optimizations, as well as some of advice on, like code restructuring and some design choices that can help you to write code in C++, which is better at size compression. And then package refactoring. As you know, we have package configs in Yocto, and so essentially that's what we're going to cover. And package selection. So package selection is all about, we have alternatives, and making those choices can also help you reduce the size. So that's pretty much agenda. If you have questions or comments, I will be on Slack, or we'll have some time hopefully at the end of the talk, and we can have live session as well. So feel free to ask questions. All right, so what I am going to show is basically a distro I maintain, which is driven out of Pocky, which is the standard distribution from Yocto project. So if you see in Yocto, essentially you will see 3 distributions policies that are available for you to use. And Pocky is the standard default distribution that you'll get when you check out, do nothing, just follow the quick start guide. But then you can choose with a distro variable. You could set that to Pocky Tiny or alt config, and then you can use one of those. So the differences are that Pocky Tiny is geared more towards smaller sizes, so it has made some distribution policy decisions that help size. Essentially, it uses muscle for C library, which is smaller in size, and it has a smaller versions of kernel, Linux Yocto Tiny. It doesn't use UDEV or systemd UDEV. It uses MDEV for device management, and it has a custom init script, which basically can run on the BusyBox shell. You could also use BusyBox init, which is similar, provides you init tab and stuff, and we'll talk about that later. Alt config is, it uses systemd for init system. The default in Pocky is 5init, and it uses LTSI kernels. But anyway, these are like the choices you have in there. And, for size, Pocky Tiny is essentially a good choice to start. You might customize it a little bit because, you might use a different kernel. You might want to use, BusyBox init or maybe sys5 init, but largely the policies it defines gives you a good framework to start your distribution. So I highly recommend it to look at the distro definitions in Pocky Tiny. All right, so how do you customize? Basically, you can simply inherit the Pocky Tiny policies into your own distribution policy or distro policy file that you're going to create. right? And you could name your distro whatever you like, and then you can do further customizations here, right? And you might want to select what you want to use to do network management, and what SSH you want to use, and there might be other things that you want to use, right? So it starts as simple as that, and you can customize from here on as much as you like. So what I did in here was I basically took few optimizations, and then I'm going to show you through those, and hopefully that'll give you an overview of what can be achieved. And I'll also discuss what are some of the things you need to keep in mind when you make those decisions. So we'll go over package selection. So in core, we support two libraries. We support glibc, which is the default, but then we also have muscle as C library. And what I'm showing you here with respect to sizes is actually just the size of the full image, right? And it is just that when you just change the C library, you are able to save a few megabytes, and that's pretty neat in there. But when you work with changing libraries, so this comes with some design considerations that you have to keep in mind. So this is a decision you make at very early stage, right? So it is not something that your boss came in and says reduce the size, and you say, all right, let's go for muscle, right? The reason is it may not be compatible with glibc, and you might have third-party code, and you might have precompiled code that is in your full firmware. So you will basically have to iterate through your support system there to make sure that all those firmwares are also compiled for muscle. So so I'm always recommending this as your first choice when you start with Yocto project. Make sure which way you want to go, or at least have that leeway where you can select what you want. There are ways to kind of bridge, some of the precompiled applications onto muscle, but then you are kind of treading, path that's less traveled. So if you understand that, yes, our system footprint needs a C library, and you have an idea of, okay, it's self-contained, we do not have any third-party dependencies where we need to worry about it, or we have a plan for that. Use BusyBox in its system. The reason is BusyBox is one in all, and it also provides a init system to you. So why not? When it is there, it's another applet, just use it. It provides you, the init levels and that sort of stuff that you had from sys5 init, but it's fast because there is no fork exec going on there. So if your system is really small, this really is very good option to start. So so I started comparing with the alt config, which means I had systemd on the box, right? And then I switched from systemd to BusyBox, and my image size went from 35 meg to 3 meg. And the reason there was that I think there are dependencies that systemd was pulling in that got dropped as well. And use mdev instead of udev. Usually on smaller systems, number of devices you have are limited. You already know, so udev might not serve as much as you would think. Udev makes sense when hardware is pluggable. It's very useful in these situations. Not to say that it's not useful in here. It is definitely, but if your hardware is pretty much contained, you could probably live without it. And that basically means that you need notifications for devices from the kernel, and you need something to capture it, UDAV might be a right option there, that can serve you. And it is limited in features, of course. You will have to look through that because there is no libudav that if you have programmed your applications to use in those APIs, they may not be available. So again, an early decision, right, at that certain point that you say, well, we stay with UDAV and we define it differently, how you want to access those. Check your global optimization flags in Yocto project. So there is a variable called selected optimization, and it is set. So there are certain defaults it has, and by default, what you get out of box is -O2 with -G, which is the most commonly used options anyway. This can basically this gives you best performance, or I would say like, best of both worlds. But then when you're targeting size, you might want to use the OS option, which is optimized for size. And once you do that, you can see that, the image size goes further down. Again, OS comes with compiler, but when you see number of packages being tested with this is small, right? Or I would say that number not small, but number of people using it as an option is small. So there might be bugs that you might find in the packages that you're compiling with OS, or there might be bugs in compiler itself. And that is one risk or one area that you have to keep an eye on when you use optimizations for size. Some packages aren't compiled regularly and tested regularly with optimized for size, and they may behave differently. A runtime, for example, compiler runtime is a interesting piece that may not work at all because it has made some assumptions about the function code generations. So those areas you might have to look at, and you might have to use O2 in certain situations on certain packages. But this is a good option to start because it ends up giving you somewhere between 3 to 5%, sometimes more, but good option to look at. So further now, I'll go over a few more advanced options that you could try. No guarantees that this will give you a lot of optimizations, but it depends on your use cases. So, and some of them might be already, OS is already taking care of, but they are options you should know. So I thought I'll just list them here. No function sections. So there is this option where you can emit every function into a section of its own, and that's good because compiler can eliminate functions, right? So if a function is unused, it's easy for linker or to find it is unused and therefore not generated in your final option. So look at this option and try to see whether function sections is the right option for you to hear. No unrolled loops. So this basically means that if you have loops in the code, don't unroll them. Loop unrolling increases the size, right? So if compiler finds you're looping 100 times, it might turn that into a loop of 25, but then execute the code 4 times in each loop, right? So, but that means that it is going to increase the code size, and you really don't want that. If you don't unroll loops, you might have to give up some of the runtime performance. Similarly, if you're using C++, don't use exceptions. You can just specify that if you're not interested in exceptions. Exceptions has runtime overhead, right? So in every unit, it has to emit those exception handlers, and that adds basically quite a bit of code to every function. F-no jump tables, that's an optimizations which basically make sure that you generate a table for all the case and case statements and stuff. So that also causes duplication because every jump table is actually going to give you this conditional codes, which otherwise you can do in loops. So these are just a few of those that I've listed here, and I'll also suggest some of the code architecture that you might want to be careful about. So if you look at like standard libraries, libstd++, which is C++ runtime library, or any other C++ library, Boost, or you name it, right? And the commonly used libraries. What do they have? They have all the functions. They are defined in the header file. So you include a file, a header file, a benign header file into your source code in C++. But then they have these function definitions inside there, right? Template instantiations. What happens? They get added to your C file, even if you're not using it. So as a result, your C++ file becomes bigger, right? A lot of people complain that, C++ code is bloated. The reason is all this, because if you use explicit template instantiations, then it will not do that. It will actually explicitly use only those templates that are being used in your source code. So it'll have two effects. It will reduce the code size, and it'll compile faster because it doesn't have to deal with all these static template instantiations that it is having there. So very important. If you're not doing it, go look at your C++ code. You might find something there. And compiler is smart at inlining these days, right? So it knows a lot more about functions and makes independent choices. When it can inline a function, it will. You could basically see if a function is being used in several places, right? Then you might want to say, hey, don't inline it, right? Because you're worried about size more than anything. If it is like one-off, okay, you might take it, right? Because inlining doesn't matter. But if it is used in like, say, more than 10 places, then you have like 10 copies, you probably don't want it. You can qualify your function with the attributes, right? And help the compiler basically say that, okay, this function is out of picture for me. A little bit more. Like I mentioned, for the standard libraries, follow the same design in your own libraries. And so do not define functions in headers, for example. The reason is same, they will become the candidates for inlining, and they will be inlined. And the common ones are like constructors, destructors, operator overloading, so they are used everywhere. So what you see then is your code getting copies of those everywhere you use them, and code becoming bigger. But if you kind of move those definitions into your source files, that is your CPP or CXX, whatever you call them, then you'll have one copy. Very important, you could also have additional annotations that will help the compiler. So pragmas and function attributes that you could use. And I highly recommend to look at them if you haven't, but a couple of them are listed here. The cold attribute, basically very interesting. It tells that, okay, this may not execute, right? So there is, it might inline it or other things, right? So compiler has information that you provided that this function is not a hot function. You can also say, don't optimize this function, or optimize 0 means optimize for size, actually. And so you could also use other attributes, but if you're optimizing for size, go for it. And use cheaper data structures, right? So if you're doing C++, use list instead of vectors, right? what you'll see in the generated code is that the code that list generates is way smaller. It might have trade-offs, and depending upon how you are doing your data structure alignments, but generally, if you're sensitive to code size, this might be a good trade-off to make. And finally, use compiler built-ins wherever possible. I've seen many places where people write their own functions thinking they are much performant, but that's not true. I've personally validated this claim hundreds of times. No, we do not know more than compiler when it comes to optimizing. It is good to use whatever compiler is providing as a built-in as an option one. And in exceptions, yes, you might want to write one, but have a very good reason to do that. Similarly, use standard C library functions. They are better optimized. So don't write your own printf or your own subset of libraries unless and until needed. Try to use the standard optimized library function. That, if you keep these things in mind, it gives a size reduction in your applications will be automatically improved. All right, so moving further a little bit, you could also get further help from modern compilers. Use link time optimizer. Link time optimizer is relatively new, and new in compiler speak is 5 years or maybe 10 years. But yeah, this is actually fairly recently done feature, and it has taken years and years. And more distributions are enabling it by default now. If you see, I think Fedora latest, I don't know, whatever version it is releasing right now, is built with LTO. So which means it is getting mainlined, being used everywhere. What it does is it basically compiles everything into intermediate code and then feeds everything into the linker, and linker calls the optimizer spec again. Because now linker has a view of the whole program, not only just one compilation unit or one file that you were compiling, it can do much better because it can do intra-procedural optimizations, right? And a lot more at a whole program level. So what you see is, it reduces size. In my case, the size reduction is few bytes. The reason is that I was only running it on one application, because back then I didn't get many of those applications compiling with FLTO. Maybe it is better now. But it is a good option to have. It can do more aggressive kind of like cleaning or removing dead code and stuff like that. And I've given some constructs here that you could use in Yocto Speak to enable it. It will work with both Clang and GCC right now, so pretty neat. Clang also supports thin LTO, full LTO. So I want to mention this. The reason is LTO will increase your compile time quite a bit. And the reason for thin LTO, full LTO is again same. You want to make a compromise between your compile time and how much juice you want to squeeze from the optimizations. One thing is that when you enable LTO, it will either need Gold linker or the LLVM linker. And right now, there is an anomaly. It doesn't work with OS. And there's a bug open in LLVM for that, but it hasn't been yet addressed yet. But it works with O2 and O3. But something to look at as you move into future. Okay, so we can now talk about some of the tools that are in the project and go over them, how they can be helpful to you. Build history. So build history, if you're not familiar with it, is noting down a lot of details about what's happening during the build. And so enable it, and then we'll see what all we can use it for, right? So you enable the build history in your local.conf, and then build an image. And there onwards, it's going to record the details about build into the build history repository. This repository is actually a Git repository. So you could basically go from build to build and back and forth. Okay, so image language, that is something that you might want to look at. This is very important that if you're not using any localization, then you may not need it. So you might prefer to keep it empty, or choose the languages that you really care about. That will reduce the data in your images, the localization data. So that's pretty neat. And there are certain image features that you might want to remove. So if it is a deeply embedded system and you're doing, firmware updates using different methods, don't use package management. It will kind of, avoid creating that package management databases in your images. Remove splash, right? So if it's not headed, you don't need splash. And for SSH, you could use dropbear instead of OpenSSH. So these are some of the, the package choices I was talking about you can make at the very beginning. But these, so for example, using dropbear instead of OpenSSH, talk to your security team, right? And ask them, is that something we could do? Because in many cases, they may not agree to use, dropbear. It may not fall into the policy or, the security policies that they might be recommending. So default tunes. So David, how am I doing the time?
You have until the top of the hours. You have about 8 minutes.
Okay, thanks. Default tunes. So look closely at them, right? One of the strong points of Yocto project is that you could basically customize what all you can use with the, how you can compile the whole image. And it allows you to choose a lot of distro or like machine features that you could enable. And for example, if you're building for 32-bit ARM, use the thumb instruction set, right? That's a 16-bit instruction set. It's compressed. You get smaller code size. You get faster performing code as well most of the time. So if your CPU, that is, because ARM has many of those, so check that. If it is supporting the thumb instruction set, use it. It will basically give you better compression for instructions just by recompiling your code. So how do you identify that? Check your default tune value, for example. And if it has this T in its name, like after the CPU implementation, then it will enable the thumb optimizations for ARM. Similarly, for MIPS, there is a 16-bit ACE instruction set. You could enable that, the MIPS 16E, that is what it is called, similar to thumb, right? And you could set the MIPS instruction set to MIPS 16E, and that will basically compile your code using the 16-bit instruction sets for MIPS as well. It's exactly similar to what thumb does. All right, so I talked about build history. And if you look at the build history a little bit, what you see is there are a few files. And I went into, so it basically is recording not only for image, but also build history of whatever it is building. So what I'm showing here is actually the build history of the image itself. And there are a few interesting files in there. There is this build id.txt, but then what you see in there is some of those dependency files, right? And they are very important. You could view them in some, .e viewer, but you could also open them in a text editor like me. And then they are basically a key value pair kind of situation, right? So A depends on B. And so you could basically track the dependencies that way. Um, and then it also lists you some files that are in the image. So you can look at what all files are going into your image finally, right? And if something sounds unfamiliar, you could then trace it back, who is adding it. There's image info, which gives you like information about what all package groups are going in there, what size it is. And then there are names, like, the image is constructed by using like, IPKs or RPMs, what have you. So those names are recorded here. So you can basically at a package level check that, yes, this package is not required. How is it coming in? And then you can trace it back. And then it lists you the package sizes in order. So you can basically look at and say, here are my top 10 packages that are contributing to size. What can I do about those? So it's a very important information when you have this, myriad of packages and where to concentrate. So this gives you a very good starting point, so to speak, where, if you can optimize your top 10, you'll get 90% of the gain in size. Okay, so just going a little bit, zooming on one of those. So if you look at like the installed package sizes, that's what it looks like. So you can see Blue C5 is about 3 meg. Shared MIME info is 2.5 meg. Do I need it on my target? So you can like ask those questions. libc, probably you have to have it in there. But then can I use glibc? This is what glibc is showing. It's about 1.6 meg. Can I use muscle, right? And how much that size will be. So, and then there are modules and so on and so forth. So it's very handy. And as I said, it has other information about the DOTI files. And this is what it looks like. And as you can see, it gives you the dependency. For example, if you look at the last, the first one, 96 boards tools is in my image, and it depends on E2FS progs resize FS. So if I haven't added E2FS progs resize FS into my image install, then 96 boards is pulling it in, right? That is the inference you can draw. And then if you want to remove this dependency for whatever reason, you can go and look at 96 boards package and decouple it. So that's the way to kind of, optimize it further. Okay, so other things, kernel tweaks. So sometimes some BSPs, they enforce all the modules because that's what their reference testing is. You might want to look at that and prune that, right? And you want to remove, no, I don't want all the kernel modules. I only want a handful of them. So add that to your machine extra recommends. Then there are a few options that you could use, and I think you'll get them in the Linux Yocto Tiny as well. For example, you could enable CC optimize for size kconfig option, and then you could use XZ compression and the config slob as well, which is kind of going to help with the memory. And you could also avoid duplicate images in kernel, because many cases you put an image in a different space, right, in a different partition. If you do that, then you might want to see that it's not generating a kernel image into /boot in your rootfs, because that will be a duplicate image. So important to look at that. And then look at your kernel config. There may be some features you really don't need, disable them. And as I mentioned, compile for small features. So I've given actually a good link here that you can look where I've done some comparisons on what it looked like when I chose different options for C library and so on and so forth in different init systems. I won't go over it, but if you have some further questions, please follow up. All right, so some future work. And I did experiment with Toybox. It hasn't yet panned out to be a full Linux system for me, so keep an eye on that one. LTO, we have started to enable it, not in Yocto project yet, but on package by package basis. On some packages, it's yielding a huge benefits, and that's very encouraging. and maybe I'll kind of, submit the patch once again for for master now that Gatiscuth is released or is going to be released. Additional compiler options, I think I discussed a few of them, but there are more that we could always talk about. And I plan to do something on Go and Rust as well. So in future, watch out for that. So that's all I had. Thanks for all your time and listening to it. Hopefully it was useful to you. If you have any questions, or do I have time? Probably no, but I can take one question or so. If not, then we can move on to Slack and we can discuss it there. Thank you.
Excellent. Thank you so much. Yes, so much information. We are now going into the lunch hour, but we could do certainly a couple questions. The first question is from Richard Purdy. Should PokeTiny enable size optimization by default?
I think it should. That will actually give a better testing for PokeTiny. So I think we should do that. Actually, many of the discussions that I had here are basically can be translated into PokeTiny default policies. Good idea.
Okay, any other quick questions? Just raise your hand. Okay, Frank, why don't you go ahead?
Yeah, so you mentioned init systems. Did you experiment with BusyBox's run it option? So there you can use run it as your init system instead of their sysv init compatible init system.
Yeah, good question. Yes, I experimented with it, and I think I still carry those patches. And I think on some of my projects, we are basically looking at run it /S6, for example, as an option. So yes, answer is yes, and it works well. I think there is a separate layer now. I think that is called metasysint. I think something like that, which houses all the init systems that are not in core.
Cool. Yeah, I'm a big fan. That's why I felt I had to mention it. Thank you.
Yeah,
Thank
yeah,
you.
no worries, I think.
Thank you, Frank. Awad, why don't you go ahead?
Yeah, thanks. I have a small question regarding the size of the image. For example, if I'm having an image in the target that has so many unused packages, and I will need to know which packages I can remove or exclude from the next build. So, do you suggest any tools that can do such analysis, or like to listen for logs or so?
So unused packages, basically what you can see is there are two ways you can go about it. One is like, ensure that you're using right packages in your, image install. But then Yocto Image Builder looks at the dependency tree fairly well, and it will add those dependencies. So if it is adding additional packages, there is a reason for that. And one of the way to go about that is you look at the image manifest that's generated, and then you have to inspect it. But maybe you are looking for something that a package or at a file level, that if a file is not accessed, then you want to know that information. Is that your question, or did I misinterpret?
Yeah, for it's about the like packages or applications, not the files. Because I don't think that there was an easy way to exclude the files from the build. This will add more headache, not optimization.
Right. So I think generally what I do is I look at the image manifest that I showed you in build history, right? And that's my starting point, to look at what's going into the image. And then then from there you can go upwards and see which package is being pulled by whom. Most of the time it's a um, additional dependency somehow that is created by package, that you have to uncouple or decouple, and then that dependency goes away. But many times people approach it like, top down, where they try to hammer it through, deleting the packages through, do root of s post processing and things like that. I highly discourage those things.
Yeah.
Yeah, so that's the wrong way to do it. Many reasons are that you are basically overriding the image builder's logic, and it's better to feed it the right thing so it does the right thing on the other side. And so it will help you when, say, the package changes. They may add additional dependency that then it will automatically pull in. But if you're deleting those packages, those dependencies will still be in there, right? Because you didn't delete those.
Yeah.
But the package would have added it, or the packager would have added it. So so doing it that way is always going to be error prone. But finding those dependency logic through build history is actually really good. Bitwake minus G also does that to a certain extent. So you really don't need to enable build history, but yeah, either of those is fine.
Yeah. Okay. Thanks a lot.
Okay, maybe one final comment. There's a discussion about optimizing for Python. Did you want to make any comments about that?
Yeah, I think we have done a bunch of stuff in there. I think briefly I can mention that we use PGO, that is the profile guided optimizer, to optimize our Python interpreter itself. And so there's a lot of details in there, on that how it is done, because generally when you build Python, it will do that because you're doing a native build. But when you're doing a cross build, you basically have to invoke something like QEMU to run the workloads and then collect the instrumentation. And so as a result, I think the Python that we generate for with the Yocto project is fairly optimized. The interpreter, that is. If you're talking about language optimizations, like how could I write better Python code, we should do another talk about that.
Very good. Any final questions? Well, thank you so much. That's excellent as always, Kim.
Thank you, and thanks everyone. Have a nice day.
Okay, we're now going to break for lunch for those of you in Europe, for breakfast, those of you in the United States. We'll be meeting back in an hour, minus 8 minutes. That'll be at 5 o'clock GMT, 10 o'clock West Coast, 1 p.m. East Coast, USA. Thank you very much, and we'll see you in an hour.
Thank you.
We'll be starting in about 3 minutes. Thank you.
Tim here, just testing my mic out.
Excellent. I was about to ask.
Yeah, sorry, I decided to reboot just in case.
So let me stop sharing. Tim, why don't you go ahead and grab the screen? 1 second.
All right.
Okay, Tim, I see the top of your head in your video feed.
Okay, sorry.
There you go.
I'm trying to get the, let's see. I've forgotten how to do slideshow mode in Google Slides.
Ross says he's going to charge you for the commercial use of his artwork.
Oh yeah, I forgot about that. Okay. Oh, there we go. That's right. Present.
Nice background.
Okay. Am I actually sharing my screen? The
Not
slides?
yet.
Not yet. This is what happens when you switch from the system you were using. There we go.
Okay, we now see your slides.
And hopefully presentation mode.
You got it.
Okay. All right, thank you for your patience, everybody. This is always fun. So this is a talk about composing reliable systems with virtualization and the Yocto project. And Christopher and I have been interacting and collaborating for a couple of years. So I'm Tim Morling. I'm the Yocto project architect at Intel, a longtime contributor to Open Embedded and Yocto project. Christopher, maybe you can also introduce yourself.
Hi, yes, I'm a software engineer and I work on the Zen hypervisor and maintain the Zen recipes in the meta virtualization layer. And I am a contributor to the OpenXT project.
All right. So we're just going to talk about why virtualization. Christopher is going to give you a pretty good deep dive into the Zen hypervisor. And I'll then take over and talk about the KVM hypervisor. We've got some additional material that I'm going to go ahead and put into the slides, but we're probably not going to cover it today. Some stuff about Acorn and Secure Boot and a few other goodies. But so I think, Christopher, I'm going to keep driving, and I'll just let you. Well, sorry. Let me go to the next couple slides, then I'll let you drive once we get to, or let you speak once I get to the Zen. So all of the content that we have here and the slides will get uploaded here as well is on GitLab. So everything we're going to be showing is actually being built and done through continuous integration, on YP Dev Day virtualization. It's a little bit out of sync right now because I've been doing some stuff today that's new. So why do we want virtualization, right? Well, our premise is the vendor kernel is dead. It is just, it hasn't been working. Greg KH is really famous for talking about evil vendor kernels. And what we're thinking instead is run with virtualization and then secure your vendored kernels if you really have to do it in a virtual machine or through virtualization. So why, right? We want to use the latest stable kernel. This is the best kernel that we as a Linux community have, right? And this could also, exclude Linux distribution kernels. They may be better than a raw mainline kernel. But their thing is that you're getting security fixes, bug fixes, new features, the latest drivers, right? And this is the reason that every single vendor out there, you should be upstreaming your changes because everybody can just get it off of mainline. Oops, I forgot to leave that. Anyway, so yeah, this isn't what I wanted there. So why else, right? We want to ship images where we have complete control over what we're shipping. So with Yocto project, we have complete control over all the contents, the versions of everything, and all of the licensing and license compliance, right? So then you can run your applications in an isolated environment on top of this base image that you ship. You might not even ship any binaries that are actually the applications to your customers. They might just download it themselves. And then you can run vendor kernels and vendor images in virtualization. So with that, I'll let Christopher start talking about the Zen hypervisor. And we forgot to change the date, sorry.
Thanks, Tim. Okay, so I work primarily with the Zen hypervisor and have done for some time. And it's a mature open source hypervisor that's been used in production for many years now. It's a project under the Linux Foundation at this point, and it has this structure that hopefully you can see in the slide here, where there's in the Zen software you have the hypervisor itself, but you also have a set of tools providing management of virtual machines on your platform, and it allows on x86 platforms allows you to run standard Windows virtual machines concurrently with Linux virtual machines. There's device drivers for the Zen hypervisor that are upstream in the standard mainline Linux kernel. And it allows you to basically do the familiar, if you're familiar with virtualization, dynamic creation and shutdown of VMs independently of one another. It's a powerful set of software. And the key thing with using virtualization is that the software within these guest virtual machines are strongly isolated from one another. There are narrow, well-defined interfaces to the platform, and guests are contained within their virtual machine. Next slide, please, Tim. So working on the OpenXT project, we leverage the Zen hypervisor to do isolation of components that you wouldn't normally confine in this way, but you can when you've got virtualization available. So we've moved the network device driver into its own domain, supported by a Linux kernel around it, and that provides network service to the other virtual machines on the system, thereby meaning that if there is a flaw in your network device driver, that the opportunity to cause disruption because of that flaw is contained to just the network device driver domain. So you're leveraging virtualization for strong isolation, and you'll see similar features adopted in virtualization-based security in Windows. It's a mature architecture at this point. Next slide, please. So this is a more recent development for the Zen hypervisor. So this is a bit of a retrospective of some work done this year within the Zen community and introduced into Yocto. Basically, we're looking at can we get the Zen hypervisor up and running on a modern Raspberry Pi 4? Let's have a go. So what we have, the ingredients for this is we're going to use the Zen support in Yocto in the meta virtualization layer. We're going to add the Raspberry Pi 4 hardware support from the Meta Raspberry Pi layer, and we'll use the Pocky standard Yocto Linux distro with the Meta open embedded body of standard software. And in order to glue these pieces together, we're going to add in an additional patch series to the Linux kernel to enable this support. And the patch series went into meta virtualization, and with the upstreaming of those patches into the upstream Linux kernel, the patch series then came back out of meta virtualization. So that was progress in the last few months. And then in order to run the build, we set a few standard configuration variables per standard Yocto build. We're going to set, say, the machine that we're going to build with. We're going to turn on the distro features for virtualization in Zen, set a couple of fields in order to speed up the QEMU build, and run a standard bitbake. And so when you run bitbake Zen image minimal, it proceeds all the way to the end and out pops an SD card image suitable for writing to your SD card and booting your Raspberry Pi. So what's actually on that SD card? So we've got two partitions. The first one contains the hypervisor, the DOM0 Linux kernel, some standard device tree for the Raspberry Pi 4, which is processed by both the Raspberry Pi firmware and the Linux kernel, and some other small pieces for the bootloader. And then in the other partition, you have the standard Linux file system, which is the root file system for domain 0. It's got all of the standard open source Zen tools, but it doesn't contain the hypervisor. The hypervisor and DOM0 Linux kernel are actually on the boot partition. It's a slightly preferable layout because you don't necessarily need those things available when DOM0 is running, so it's better to put them on the boot partition. Okay, so when we launch, this is what you'll see if things have gone well and you've got a SD card that's healthy, and all the way through to complete boot. It's a little underwhelming, but actually it's highly reassuring to see this as a console message rather than frequently hypervisor engineers see much more exciting log messages than this, but this is good. So when you log in, it looks just like you're interacting with normal Pocky Linux boot, but actually you've got the Zen tools as well. So what we're seeing here is using the XL standard Zen command line tool to list the running domains on the system. And you can see domain 0 with a 256 megabyte memory allocation. It's got 4 virtual CPUs. Everything looks healthy. So there you go. That's success. So to get slightly more exciting evidence of what's going on your system, you can get for yourself one of these USB serial things from a popular auction site. And so this plugs into the USB port on your laptop or nearby desktop machine, and you plug those 3 wires that you see hanging off the other end onto the pins off the Raspberry Pi 4. Actually, Tim, if you can move to the next slide. There we go. So it's these particular pins, and then you turn the power on your Raspberry Pi 4, and if you're running Minicom on your laptop, you can watch all the serial messages as the Raspberry Pi 4 launches, and that will give you, the startup of the hypervisor and the transition all the way into Linux and DOM 0. So I think if we go to the next slide, Tim, I think we've got a video, if that will play. Here we go. So takes a little bit for the, here we go into the bootloader. You can see it's loaded Zen. It's got a slightly different device tree than standard Linux to put things in the right place. And there we go, all the way through mounting the root file system. It's getting a IP address on the network, and there you go, all the way to the root prompt. Thanks. Okay. So once you've got Zen up and running, again, the standard Zen functionality you might be familiar with from other Zen systems is available. You can see what VMs you're running. You can query info about the hypervisor. You can examine the Zen store state and look at the kernel messages and the Zen boot messages, all standard stuff, and all now working on the Raspberry Pi 4. So once you have a hypervisor on the Raspberry Pi 4, the next step of interest is to get yourself a guest virtual machine to run. So again, there is a image recipe in the meta virtualization layer for building a guest operating system. And so it's configured differently than the host. There's things in DOM 0 that you don't need in the guest. There's drivers in the guest that you don't need in DOM 0. Anyway, so you just bit bake the Zen guest image, and it will insert the correct pieces. And the output of that you'll have a file system that by standard, the default will be to produce an ext3 file system that you can then use for launching the guest. So you'll need the copy of the file system and the guest kernel image and a config file in order to tell the tool stack where those pieces are. Okay. So in addition to that, there's a little bit of preparation you can do to DOM 0 on the host to enable networking functionality within the guest. So this is a sequence of steps that will create a new bridge in DOM 0, and it will move your Ethernet device onto that bridge, and it will shift DHCP over to the bridge from the raw interface. And then the second step, as preparation for launching the guest, is to make that ext3 guest file system available through a loopback device. It's a little cheaty to do this, but it's definitely convenient. Okay, so this will show launching the guest from domain 0. So we're using SSH to access the host from the desktop machine coming in through the network, and then we'll run the command to actually create the guest, and we use the -c argument in order to follow the serial port as the guest starts, the virtual serial port of the guest. So you see here all the Linux boot messages as the guest is starting. This is a standard Yocto kernel built for the guest, and there you can see that the guest itself has got its own IP address from the network there, and then we just power off the guest and it shuts down cleanly, and you can see that the guest is no longer running. Okay. So this is a description of some of the work that was involved in the new patch series for Linux to make Zen on Raspberry Pi work. So this was some of the work done in the Zen community to enable compatibility between the Raspberry Pi 4 hardware and domain 0 for Zen. In order to bring this into Yocto, we used some of the more novel aspects of bitbake and layer functionality. So we used a dynamic layer inside Meta Virtualization that only activates when you're using it in conjunction with Meta Raspberry Pi. And then within that dynamic layer and that extra set of recipe additions, you've got the patch series that modifies Linux for Zen, which is now upstream, and that's come out again, no longer needed in Meta Virtualization. There's also some customization of the bootloader script so that it loads the Zen hypervisor binary. By default, the U-boot bootloader would just load a Linux kernel, so we have to add a script to launch the hypervisor first. And it sets things like the DOM0 kernel command line, which has got some Zen specific settings, not typically there for standard Linux only boot. We add a config for the Zen hypervisor uses kernel configuration, kconfig, similar to the Linux kernel. So there's a file in there with the right settings for the Raspberry Pi 4 hardware, and some other small additional pieces. I think that's all I want to talk about on that one. So I just want to give some other pointers to other hardware that you can also use Zen with via Meta Virtualization. There's so you can build Zen for a standard x86 platform. There's integration with Yocto's WIC tool so that you can run this command. It will generate from the Zen image minimal, which is the host Zen image. It will generate a single file that you can just DD to the front of your disk to boot. So it has the partition layout and bootloader configuration just to launch straight into Zen, nice and easy. There's another piece of hardware that people in the OpenXT community rate as suitable for Zen development, which is the PC Engine's APU2. It's a little small device, but good open hardware, and has support for dynamic rooted trust for measurement. If you're interested in that, I would point you towards the OpenXT community to come talk to us. And then a final way of launching Zen in Meta Virtualization is to actually use QEMU. So the bitbake run QEMU command, you can launch the Zen image minimal, and it will launch Zen at your command prompt. I'd say this is pretty experimental. It has worked. It's kind of stretching both QEMU and Zen a little bit. So maybe in need of a little bit of love. It might depend carefully on which machine you're launching, or which exact version of Zen. But that's a thing that there's a few of us interested in polishing a bit and making
And
generally. Sorry, Tim. Go ahead.
It's also interesting because you can do TPM in QEMU now too, and so there's a lot of really interesting things you can do without having to have that hardware, quote unquote.
Gotcha. Yeah. Okay.
I think that's it for that part. So I'm going to take over here and just talk a little bit about some of the new things we've been working on for this round behind the scenes. So it'll come to no surprise to many of you, but I use costs a lot for what I call the manifest and configuration. So manifest meaning what layers am I using, and configuration meaning, you know, what am I doing in local.conf and things like that. And the other thing is to show off an approach of using multi-config to build the host and the guest images at the same time, right? All in one step. This is still a work in progress. So, you know, we're gonna have to update it to be exactly what we want, but it actually works and builds the image. It's just not quite as functional as we want it to be just yet. So there's a lot of stuff here. I put all of this material here just so that people can go back later and look at the slides. I'm not going to cover everything, but costs basically is a tool that came out of Siemens, even though it's not a Siemens specific thing in any way whatsoever. And essentially it just lets you lay out in YAML what your configuration is and what your layers are, right? So it's got certain things it needs this header, but here you can set your machine, you can set your default target, you can set your default distro. And then you can start adding your repos. And one of the interesting things is it has this meta custom. So this isn't an actual layer. You're not actually naming or creating anything. This is just what's in the repo that you are running costs from. And so in that repo, you might already have a conf layer and, you know, conf multi-config and things like that. And all of that will just automatically get picked up as this, you know, meta custom entity. And then you can start specifying the other repositories and layers that you're going to use. So here you can see we're picking up Pocky and, you know, where we're getting it from. In this case, we're just going to grab master as the ref spec. So ref spec could be Dunfell, or it could be a very specific commit hash. So you can completely control exactly what you're cloning. And then you can, in the case of Pocky and some other layers like meta open embedded, you've actually got multiple sub layers. And so you can specify all of the layers that are being added. And then we can add meta intel, meta open embedded, another example of multiple sub layers. We can add meta acorn, meta virtualization, meta cloud services, meta security. So one of the things that might be considered a drawback is you can only do your repos in one kind of root-based cost YAML. And so that's why everything is in here, even though we might not be using all of it for the specific build we're talking about. And here's Meta Raspberry Pi. And then you can start doing things with BB layers, right? So this stuff will just get, the stuff under BB layers conf header, this will get prepended to your BB layers file. So you don't have to tell somebody go edit your BB layers or go run this command or that command. Same thing with local.conf. And so in local.conf, we can do our normal things, but here we can, you know, distro features append virtualization, right? So then the next thing is you can actually inherit or include from one file to another. And so here's what we're doing for Raspberry Pi. So we're including the cost YAML file that we were just talking about, but now we're changing the machine to be the Raspberry Pi machine. And now we're adding a target. And notice I'm using multi-config. I wasn't sure if the new MC syntax works the same, so we'll have to verify that. But so this is telling COS, first I want you to go build the Zen guest image minimal, and then I want you to build the Zen image minimal. And then you can see some other changes. So here, because we're building a whole bunch of different things, I want to change the temperature to be something where it's kind of obvious which build what I'm actually looking at. And then some things about, you know, the image file system types that we're going to add. We're going to append the Zen feature to the distro features. We might want to set the number of threads or, you know, parallel make. Might want to change those QEMU targets that Christopher talked about a little while ago. And then there's some extra stuff here. This is what I'll get to in just a second, talking about this Zen guest that we're going to build. So this is actually work that Ross Burton originally did on the Meta Acorn layer. I changed it from being a container package to a vessel package just because containers is so overloaded in our terminology right now. But basically what these two lines are doing is setting up a BB class that's going to allow it to know where to go grab these things from in order to shove it into the host image. And then you can see I'm actually going to append in the Zen image minimal this Zen guest image minimal package, right? So what this is just a recipe that wraps that image and makes it installable onto the host image as a package, as an RPM or DNF or a IPEC or whatever. So what's that multi-config look like, right? It's really simple. And so this is literally in the YP virtualization layer that we've got. We just set the distro, set the tempter, set the preferred kernel provider, and then in this case we want a QCOW image. So that's a common cloud format, which is basically directly bootable. In theory, right? So this is not working right now. That's why we got the under construction. We're probably missing the right WKS file or the WIC Kickstarter file and maybe some other things, but more on that in future updates to the repository. So we've got this this need for packaging something up as a guest that we have built, and packaging it up and then installing that onto the host image. And so here we're just defining some variables and some things we're going to use. And we do a little bit of magic with the image name. We set what the vessel dir, where these things are going to be put. So right now it's going to go into varlib machines. More likely we'll probably start putting things into varlib libvirt images instead. Just kind of standardize on the libvirt directories. And so we're going to depend on kernel deploy. We want to make sure the kernel has been completely built, and then we're going to depend on multi-config being done. I've had some comments from other folks that maybe the kernel deploy isn't necessarily needed, but in this case, at least we know we want do image complete. So that means the WIC image has been done, the post-processing has been done, and so on. And then do install, we're just going to create that vessel directory, right? Just in case it doesn't exist already. We're going to, in this case, copy the image. So this is the kernel image because we need that in Zen. And then we're also going to install that, the actual root FS, and hopefully that'll be a QCOW. So this installs it. It just doesn't boot right now. So a little bit of caveat emptor at the moment. And there's just a little bit more. We're inheriting a package group, or wait, I think this is the wrong. I think this is the package group file. Sorry. The title of the slide's bad. Yeah, this was the Zen package anyway. Let me skip over that. So the Zen guest image package, this is calling Zen guest package BB class, which is what the prior slide was meant to be. So the BB class, or sorry, what the couple slides ago was showing. So what we're going to do here is use that Zen guest packaging class just to package up this image once it's built. We're going to go ahead and pre-populate that static config file for Zen and just install it alongside the image. And here's what we're currently working on with the Zen configuration file. So you'll notice that the kernel is going to be in the same directory, this varlib machines that we're using. The console settings, the memory, 256 megabytes, the name of the guest, how many virtual CPUs it's going to have, the serial port. And then here's where the magic is kind of happening. So we're going to use this QCOW2 format. So essentially we're using the QEMU driver stack in Zen. And we're going to load this QCOW2 format, make it into a virtual device, make it read write, and the target will actually be that QCOW image that we're installing. And then finally, we need to have the virtual network interface set up. So at the moment, we still need to use the bridge control, BRCTL, in order to create this Zen bridge device. And even with trying to set up things, in this case, we're using sysvianet. So even trying to set up the interfaces and whatnot, it still needed the device to be created. So we still need to use that BR control that Christopher talked about earlier. So we've got a little bit more work to do here to make this, directly just out of the box work. Christopher, I'll let you go back.
Thanks. I just wanted to give a few thanks to the different groups that have been involved in enabling the Zen on Raspberry Pi 4 support and making it work. So it's been nice to see the collaboration that's been happening between different groups in the Zen community upstream, and in particular the interest from the Eve project, where some of the original enabling patches were first put together, and then the support from the maintainer of meta virtualization, Bruce Ashfield, for allowing some of the more unusual modifications to the meta virtualization layer to go in, and respect to Corey Mignard at Monitor Vista for first coming to the list with the proposed set of patches to enable the Zen on Raspberry Pi 4 work. That was sort of precursor work to what got merged in the end, but it was definitely a strong contribution and very helpful. Thanks to Tim and David for giving us the opportunity to talk at the Yocto Dev Day about this. Also, thanks from me to the OpenXT community for supporting my involvement with Zen and Open Embedded. And lastly, a quick thanks to the Raspberry Pi community for developing and promoting accessible hardware with open source software. It's fantastic. So,
yeah, definitely echo that. I've had some issues personally with Raspberry Pi just because it isn't open source hardware, and I wish it was. But the fact that they keep coming up with these new boards and new versions it's pretty hard to ignore it, and it's very, very popular right now. So. Yeah, so now I'm going to take over and talk a little bit about the KVM hypervisor, and then I'm going to try to go fairly quickly to leave some room for questions. So KVM's just built into the kernel, and it basically just uses QEMU to run it. And what do we need to do, right? So we create a package group that sets up the tools we need. So we need core boot, we need QEMU, we need we're going to use libvirt on the target, or sorry, on the host, right? So, or yeah, the target that's hosting KVM. One of the things we want to add here is actually cloud init, but it isn't ready to build right now. I'll talk about that in a second. So just like we talked about with the Zen, package, we've got this KVM package. But in this case, I thought I'd do something a little differently and show how to actually grab a unmodified binary image and deploy that. And again, this is based on work that originally was done by Ross Burton with Meta Acorn. So here, what I'm doing is I'm setting the base URL. So in this case, Ubuntu, right? So Ubuntu just has this cloud images URL and you can go to, and then you need to know the release. So in this case, focal is 2004. What's the arch going to be? AMD 64, because I'm going to run this on a Intel platform. And then what's the name, of that image going to be? And so it's basically, focal server cloud image, AMD 64 disk KVM image is what the thing is. And then I can set a date if I want a specific build, but they're constantly updating this. And so it's better to just set it to current, and it'll just grab the latest image, which may even be nightly, and then just, make that whole thing into a binary that we're going to install. And so, here's what the source URI ends up looking like, a little bit of magic to get the SHA-SUM from Ubuntu. And then I've got this function, just to go fetch the checksums and go like hack this into figuring out what the source URI checksum is actually going to be. And since we're downloading this from over HTTPS from Ubuntu, we should be able to trust that checksum. And again, this is credit to the insanely wonderful Ross Burton who showed me how to do this a few years ago. And then in the last time we talked about this, we didn't really show a nice way to launch. We definitely want to do this a different way, but right now you can basically just call, like you would on your development machine or your desktop, just call QEMU system x86-64 with the amount of memory and the drive, and then here we're going to use something that should look kind of familiar to that Zen format that we talked about earlier. So we're going to grab a QCOW image, and it's at this place, and we're going to run it no graphic because this happens to be a console only image and a console only server image, so we don't need graphics. So with that, this is me just capturing a PuTTY terminal. So you can see here I run that launch script. So this is me using a serial console to the NUC that's actually running all of this. And now you can see that Ubuntu 20.04.1 LTS booted. And this doesn't quite get all the way to the login. I had some trouble with the GNOME shell recorder, but it's basically not that exciting because it's just booting. But the next part of this though is that the default images do not come with a password. So they come with a default user of Ubuntu, but they don't have a password in them or SSH keys in them. And I'll give a caveat, right? I am not like a cloud person, not really, right? I'm trying to do this virtualization stuff because this has been hitting the edge and embedded very, very hard for like the last 4 years, right? We've been watching this coming for a long time, and multiple people are doing this commercially, but not necessarily sharing it with the community. Okay, so just some future work here. And in the slides, I've actually got a bunch of stuff about Secure Boot, just some things I learned. I'm not going to get into it. We want to add cloud in it because that's actually how you set the username and password. This is what everybody is suggesting. We want to use Versh to actually use a template to create an XML template that's how you would normally launch with libvirt, or another launch script that's kind of auto-populated rather than the one I showed you, which is hard-coded. And also a lot of people insert their SSH keys into the guest, and that's also, I believe, done with cloud in it. Again, I'm not a cloud expert. So I'm going to stop there because we've got a lot more material that I'm going to leave in the deck, but that's really what we wanted to cover today. I'm leaving the stuff in the deck because I just figure it's, hey, we're doing this work. You guys might as well see what we're doing and go and then ask us questions on the mailing list. But we've got a couple minutes left. Does anybody have any questions now?
Yes, please raise your hand and we will mute you. So Frank, why don't you go ahead?
Hi, I'm trying to better understand the use case for VMs in embedded. Like, I know that the vendor kernels are buggy and lagging behind.
Yeah, no problem. I can answer that in a lot of ways. Okay. So I work in the Internet of Things group at Intel, and so we have a lot of customers, including industrial and retail and hospitality, that are actually running things virtualized, right? So for instance, in industrial, people are actually running software PLCs in virtual machines now. So they're replacing multiple old school PLC devices with one, Xeon D or whatever it is, and running virtual machines with real-time interrupts and things like that. And in retail, they're also running clusters now of machines that are basically like auto-populated, right? They're running like Pixie Boot. Essentially, we actually like ship them devices that have some trusted, stuff installed into them, but they basically plug it into their network, turn it on, and it immediately downloads an image and starts functioning. And so what are people doing with that? They're doing inventory control, RFID tags, barcode scanners, front line point of sale systems, inventory tracking stuff. They're doing actually order fulfillment systems where robots are grabbing items and actually putting them into the order and bringing it out to the front desk to be picked up for curbside delivery and things like that. And the reality is, like, every single thing I'm talking about, all of this is containers and virtualization. People are definitely running some stuff on bare metal, but it's almost becoming only to launch the virtual machines, right? So now, I talked about Xeons, but the reality is you can do this on a lot of other machines, right? So at some point, once we get to the really, really low end that we all know and love, virtualization is not going to work, right? The old MCU class machines can't do that, but the chips, the SoCs we can get, especially now that these fairly amazing, ARM64 platforms that like powering the Raspberry Pi are coming out, and the RISC-V systems that are coming out, and obviously the classic Intel ones, the Atom processors and things like that. There's just a lot of capability there, and they can absolutely run things as containers. And if you're running Podman and Cryo and things like that, really, really lightweight things, not necessarily Docker, it's pretty amazing what you can do. And so the world has just moved on, and people are no longer doing the classic full image installation like they used to. So this allows, it's an update mechanism as well, I guess is another way of saying that.
So the host OS is the vendor kernel, but
no,
everyone's running their software on a VM, and so that's what they want to deploy to is a VM.
Yeah, and what we're saying, what Christopher and I are saying, right, is like build the latest stable kernel mainline with maybe a few of your own, hardware tweaks, but hopefully as little as possible, right? And that's actually what the quote unquote host should be. And all of your, funky weirdness that the smelly fish that you're sorry you still have to run, that goes into the virtual machine or the containers.
Got it. Thank you.
Any other questions? Yeah, I think we're at time, but
I got one last question.
Yeah, go ahead.
Unikernels, there's like Mirage and Firecracker, it's like this Rust thing. It's like it's not I think it's kind of a Linux. I mean, is there like support in Yocto for booting these kinds of things and instead of as VMs rather than booting Linux?
Do you want to take that one, Christopher?
Sure. Yeah, so I mean, Tim showed a recipe for basically downloading a Ubuntu image, grab the binary, validate the SHA-256 summon, and then, launch it. So I don't see why you can't do exactly the same thing for your Mirage image or whatever payload. If the hypervisor's equipped to launch that kind of workload, I think Yocto has the ability to support you writing a recipe to do it. So
yeah, like Alejandro gave a talk about bare metal, building free RTOS. We've got a layer for building Zephyr. Bruce just gave a talk about RunX for containers that have a small micro Zen VM in them. So don't think of Yocto as being only Linux anymore. It's really a bunch of tools for building things to run your software. And there's really nothing you can't do. It's just a question of whether it's already implemented or not.
Cool, thanks.
I think we should yield the floor since we're beyond time, I believe.
No, actually, we have 3 minutes left. Sean Desai, you have a question?
Yeah, guys, thanks a lot for the talk. Just quick question. Now that Tim's mentioning things where containers are now possible on embedded systems, would it be very easy in your perspective or in your experience to get updates, for example, over-the-air updates, or let's say some form of version control on these kind of applications? Would it be as easy as, let's say, Docker pull, get the latest image, and bam, next thing you know, it's all up and running? Or would it be quite difficult?
I won't say it's like super easy, right? So there's multiple vendors doing this now. So Foundries.io does this, Balena does this, Rancher OS Rancher that was just acquired by Suzy does this. So there's a lot of these almost pure Docker or pure container OSs where what we've been calling the host, all it's there for is just to just to run the containers. But as far as over-the-air updates, this is a really touchy subject, right? Because some people only want to ship an AB image where they flash the entire OS, everything. Some people want to go ahead and allow, with secure connections to allow those containers to be updated. So it depends on your use case. So in the case that I was talking about earlier with, land-bound systems for retail, those things almost exclusively run in very aggressive update modes with containers. The industrial machines and transportation, are very conservative about updating things because you don't want to crash your entire robotic line or your airplane or your train or your car. And so it just depends on your what you can handle in terms of your attack surfaces and your robustness and reliability and all that. But I didn't talk about it and didn't have it in the slides because it's not ready yet, but we're actually building Kubernetes as well in a host image or target image. And then we would use some of the stuff talked about earlier this morning to build OCI containers or package up traditional containers and put them on the target. And with that, time to go to the next one.
Thank you very much, Tim and Christopher. Excellent. Okay,
can you hear me?
Trevor, you have the floor.
Can you hear me?
Yes, I can.
Okay. Well, welcome. Our talk is, so you just heard from Tim. He's going to be in this talk too. This talk is on CI/CD for Yocto project maintainers with Kubernetes and Tecton pipelines. So brief introduction. I'm Trevor. I've been working at Wind River for a little over a year now. I'm primarily in user space. But lately I've started working on some infrastructure stuff as well. And Tim is a Yocto project architect at Intel.
Trevor, could you raise your volume a bit?
Sure.
On your microphone, yeah.
I always have this issue.
Yeah, so while he's doing that, or is it fixed now?
I'm Max. Can you hear me?
We'll work with this. Go ahead.
Okay. So both of us are MetaPython maintainers. So it's on the MetaPython layer for Yocto. Also very excited about Kubernetes and Tecton being used in the Yocto context. So the agenda for this talk, we're going to hand it over to Tim shortly, and he's going to talk a little bit about the state of Yocto CI/CD as it is now, and he's going to talk about Kubernetes and Tecton, the whys and hows, and then I'm going to take over again and talk about a bit about some pipelines that I've implemented, talk a little bit about shared state, some tools, and some future work, and there's also going to be a demo video in there. Disclaimer before we jump in, so we're Yocto experts, not necessarily Kubernetes experts. Suggestions are always welcome. I actually just got started with Kubernetes a couple of months ago, and The other thing is that we're focusing on a single node developer setup. So everything that I'm going to be talking about code-wise is intended to run on a single machine, but because it's Kubernetes, it's very scalable. So I'll hand that over to Tim.
Yeah, so just want to talk about like where we are and where we've been, and let's go ahead and just talk about the Yocto Auto Builder and things like that. So, for people who don't know about it, the Auto Builder is based on the BuildBot framework, and over the last couple of years, we've completely refactored it to basically run on top of vanilla BuildBot. A lot of work by Richard Purdy and many others. In the Yocto project itself, the community project, we've got, I believe it's 12 bare metal machines that are all running it. It can absolutely be containerized. I've done some proof of concept of that, but so there's a few things, right? The Yocto Auto Builder has restricted access, meaning you have to be given an account to actually start any builds or to do any SSH, and that's okay, right? You want some control. It's really, really incredibly useful and powerful, but it's probably overkill for the average developer workflow. And the code that's behind it right now is very specific to the Yocto project and what we have in our cluster. Next. So, there are homegrown auto builder instances. I've done it. Trevor's done a couple. I think other people have done that. If anybody watched my Living on Master talk a couple years ago, I talked about Jenkins. But I really want to highlight there's security issues there, right? Underneath it all, it's Java and a bunch of Java libraries that are actually not being maintained at all and bit rotting. So please do not do any new work on Jenkins anymore. Please don't. Okay. There's Travis CI, all the crop stuff all runs on that, and I've done a lot with that. And right now, all of the Yocto Project Dev Day stuff and the MetaPython 2 layer, which I'm not going to be supporting anymore, that's all done through GitLab CI. Then there's other stuff. There's Circle CI and so on. Next. So just a little bit about Kubernetes and Tekton and why. So, this is containers all the way down. Kubernetes is a container orchestrator. It's the one that has basically won the war, right? So Docker Swarm is no longer really being developed, and there's a few others like Chow and whatnot that just aren't being supported from the Cloud Native Computing Foundation. It's application agnostic. You can do whatever you want with it, really, like seriously anything. It supports several different container runtimes. So we're currently using Docker and Containerd, but it also supports Cryo, which comes from Red Hat and doesn't use Docker at all. It's a little bit more lightweight. And if you want to find out more about it, you can go to kubernetes.io. Next. So why? Okay, it's everywhere. Everybody's using it. It's incredibly highly scalable. There's a lot of existing use cases, extensions, and services. A lot of people developing code on it. And it really provides a set of building blocks that you can adapt to whatever you're trying to do rather than like a specific tailored solution. So we'd kind of say, the auto builder is a very specific tailored solution as an example. And a lot of people have been doing containerized builds more and more and more. So why not go ahead and use Kubernetes, or K8s as it's called for short, for that? Why Tekton? Well, if you're going to use Kubernetes, why use Jenkins to call a Kubernetes job, right? Why don't you use Kubernetes to call a Kubernetes job? So it's a continuous integration, continuous deployment framework for Kubernetes, which adds tasks and pipelines and actual instances, a task run, a pipeline run, event listeners so that you can, respond to Git or whatever, Git changes or things like that, and then templates for triggering and bindings for triggering. And you can look at tekton.dev to see that. This basically came out of some work that I've been doing with Kernel CI and Kevin Hellman and folks like that. And we found out about Tekton being just incredibly customizable, relatively easy to understand language. It's actively under deployment or under development, and it's really modern and using all these kind of modern cloud technologies. And just like surprisingly, it has this really rich dashboard and command line interface that's just been kind of a pleasure to work with. Next. So I'm going to let Trevor take over now.
Yeah, so the server that I've been doing this development on, I have a home server. It's the only node in the cluster. I've tried out other nodes, but it's currently the only one that's running. It's got 20 cores, 64 gigs of RAM, running Fedora 32 server. Kubernetes on the server was set up with kubeadmin, not Minikube. The reason for that basically being, Minikube is a great learning tool, but kubeadmin gives you a lot more control over the setup. And when it comes to certain, networking stuff like exposing the Tecton dashboard, for example, on a node port, Minikube starts to become a bit of a hassle, and it's much easier to do things at that point on kubeadmin. So Minikube is a great learning tool. It was what I started on when I started learning Kubernetes, but I have since moved on to kubeadmin, which I find to be much more powerful and actually accessible. So the end goal of all this, we want to be able to run build pipelines and test pipelines and be able to view them on a dashboard. And the image here might be a little small, but this is a screen capture of my dashboard running on my machine, showing a completed build from my MetaPython pipeline, which we'll get to shortly. So how do we get to that end goal? So I've got some code posted on GitHub. It includes setup instructions for setting up your Kubernetes cluster and a bunch of example pipelines. This is actually already in use in the wild. As a MetaPython maintainer, I'm actually using this to do builds twice a day to keep track of patches that people are submitting to the mailing list. So we'll start with a simple pipeline, just talk a little bit about how this is implemented. So the concept of this pipeline, so as a maintainer, when I started looking at this, I was thinking, basically what you have to do is keep an eye on the mailing list, and whenever someone submits a patch for a particular layer or several patches for a layer, you need to be able to build them, validate them, and then sign off on them. So what I started doing with these pipelines was identifying a delta for all the patches between master and master next, getting a list of corresponding recipes, and then sending them to Bitbake and building them, and then reporting whether it passed or failed. So I have a very basic pipeline written for Pocky. It's all manually controlled, unlike the next one I'm going to show, but it does work in the sense that it will go and build a small number of recipes, and I'll get to see if they built successfully or not every time a new patch comes in. And I've got a couple of screen captures here, just as an example of what the YAML files that you use to implement these pipelines might look like. So on the left, I've got a task for setting up the workspace. So you can see at the end of the day, it's all really just bash scripts, but wrapped with some extra information for Kubernetes. And on the right, I've got an example pipeline. So it's really very simple. There's just a couple of tasks that you list out saying, I want you to run this task, and then I want you to run this one after after a certain task. And that's really it. There's not really that much to any of these files. And these can be instantiated on your cluster with a couple of commands. So I'm going to have a demo video for this in a bit, but I'm going to talk a little bit about the MetaPython pipeline. So it's the same concept as the Pocky pipeline. This is actually the meat of the code that I've written and where this all started. So for a little bit of context, when I started as a maintainer for MetaPython, I was manually building everything. So I'd check the mailing list a couple of times a day and see what patches have been submitted, make sure they were on master next. And then I'd pick out all the packages that had new patches submitted, and then I'd build them with Bitbake, make sure they worked, and then run test image to make sure everything was okay. And then I'd go back to the mailing list and sign off on them. And then that was, didn't take a lot of time, but it was very manual and prone to error. So internally, I started getting familiar with Kubernetes and Tecton and started putting together a pipeline. And so I've got this running now. Again, it runs twice a day, makes maintaining MetaPython way easier. Tim and I have been talking lots about getting this extended and include new features. Like right now, we can't run test image because I haven't been able to get a virtual machine running inside the containers that all this is running in, but that's coming. That's something we're actively working on. And if you want to look at the code for this specifically, you can go to this link. I've got some more examples of what that looks like, but first a diagram that Tim put together. So this just kind of shows you what's going on. So the difference between the MetaPython pipeline I've got posted and the Pocky pipeline I've got posted is the Pocky one is manual. So there's a handful of files there you go and you say kube control apply -f and then the file name to start them up in your Kubernetes cluster. With MetaPython, what I've done is I put together a cron job that will send an empty post to an event listener resource that will then send a trigger template that knows to start the MetaPython pipeline that will then in turn run the setup workspace, build task, and log task steps, and then report them. And the log task actually runs conditionally on whether or not the build task had anything to do. So you can see on the left there that he actually labeled that there are 2 different paths to the pipeline.yaml. And what that means is that you can instantiate a pipeline run yourself manually. It does essentially the same thing as the trigger template does through the event listener, but they're kind of mutually exclusive in the sense that if you've got the trigger template running, you don't really need to ever start the pipeline run yourself because the trigger template does the same thing. So just a couple of more examples of what these look like. So the MetaPython build pipeline, there's a couple of tasks listed there. You can see how they're ordered, and you can actually see the conditional check to see, did MetaPython build have anything to build? And if it says yes, this is actually just a file that Tecton puts somewhere. If that file has a yes in it, then it will go on and start the MetaPython log, which is really just a placeholder log step, but it is there. You can see an example of pipeline run, which has some hard-coded paths from my machine, but that's something we can modify later to be more modular and use what are called config map resources to simplify that and make it easier to use on different systems. But again, I guess the message here from these images is that none of these files are really that complex to get through. They're pretty short and they're very easy to modify for your own purposes. And just a couple more is showing you the trigger template again. So if you look at the difference between the trigger template and the pipeline run, so on the right here and on the left here, they're essentially the same content. It's just the trigger template is what is actually spit out by the event listener. And on the right, you can see the cron job, which is a Kubernetes native resource that twice a day will just send an empty post again to the internal address for the MetaPython event listener, and it'll start up a build. So as a final thing before we get to the demo, just as an add-on, there's actually a third pipeline, which I'm not going to detail as much. Again, this is all available if you want to go look at it, running an automatic shared state. So what this does, it's built very similar to MetaPython, and it just goes once a day and runs, builds a handful of images from the Pocky repository to have available as an S-state cache automatically for other builds that are running in the Kubernetes cluster. And it uses an S-state mirror pointing at that. This final thing for the demo. So there's some useful tools out there for Kubernetes. A few of them I've shown off to Tim, and we've been discussing this again. There's a little bit more work to be done in this area. So K9S, I'll show that in a moment. What that is it's a command line interface similar to like HTOP for kind of managing your Kubernetes cluster. You can use it to look at Tecton resources, but not necessarily view the logs directly for those. So there's a little bit of limitation there, but it can also be extended. So that's something that will be possibly added in the future. Helm is another great resource, but it has its limitations. So what it is it's essentially a package manager for Kubernetes. It allows you to quickly deploy a bunch of resources and example deployments, but it doesn't seem to be all that compatible with Tecton. It doesn't like some of the resource definitions as far as I can tell. And then the third and final tool that I wanted to mention is the Tecton catalog, which is actually really cool. So what the Tecton developers have done is they've put together a bunch of templates for all sorts of stuff that you might want to run as tasks in your Kubernetes cluster, like checking out a Git repository or running a command in your AWS cloud instance or something like that. So I'm going to show a demo video here. hopefully this is large enough. So what I'm going to do, you can see me running kube control to get.
I think we just lost his mic. He was concerned about that. So basically, he ran kube control to get the cron up. Are you still here, Trevor?
Yep, I think I cut out for a minute.
Okay.
Yeah, so what I'm doing is I was checking the cron jobs in my cluster to see what happened, and I could see that one had started a little less than an hour before I checked. So I manually started it by running a container in the cluster and just sending the post message myself. You can see on the top that this is the Tecton command line that is just spitting out some, if you spend any time with Yocto, this will look very familiar. It's just running a build. And on the bottom, you can see me kind of paging through different resources in K9S just to show what the tool actually does. Like I'm just looking at the definitions of different stuff there. In this case, the MetaPython event listener. And as other talks have done, like I've actually had this pre-built ahead of time so that the pipeline would run very quickly. And then it's done. So hopefully that's pretty clear. I know that's a short video and I go pretty quickly there, but that's also available on the repository if you want to take a look at that. And here I am now navigating to the Tecton dashboard and just looking at the same pipeline that just ran. So you can see the equivalent output, but in the context of the dashboard itself rather than looking at the command line. They both show the same information. I'm actually more inclined to use the command line myself, but the dashboard, like Tim was saying, is very rich. There's a lot you can see there. It's very useful. You can actually, if you look in the top right, you can also run pipelines yourself from the dashboard if you want.
Now I think it's just looping again. Yeah.
Yeah. So future work. So as I mentioned, Tim and I have been talking a lot about this, and frankly, there are dozens of ideas we've got going on for next steps to take. But one of the big ones is using trigger binding secrets and config maps. That's something that isn't there right now in any of the pipelines. Everything's pretty hard coded, and we can use these extra resources to do everything from avoid hard coding paths to setting up names of recipes or layers we want to build depending on how advanced this gets. There's proper ingress. So right now, what I do with the Tecton dashboard is I expose it as a node port so that I can view it on my local network on the server, but ideally put together some, an Nginx ingress controller that will actually route traffic and handle exposing all that better. Tim
and that's all a bunch of Kubernetes speak. So if you guys don't know what those terms are in those first two sentences, just go look it up on Kubernetes. They are Kubernetes specific terms.
Yeah.
Go ahead.
Tim has been talking about trying it out on AWS or Google Cloud. And if you were watching the previous talk, you've seen that he was into virtualization. And I've kind of been talking to him a lot about potentially coming up with a solution for test image. So one of the problems that we're having right now, as I think I mentioned earlier, is the pipeline should ideally do the builds for all the packages and then do a MetaPython p-test image, do a test image on that. But I haven't been able to successfully get test image working inside a container, even using Slurp and without KVM. So we might have to resort to using KubeVirt or some other solution to get that working. It's entirely possible that I've just been dancing around the right configuration in the local.conf file and the whole time, and it was easy, but future steps. And Tim, I if you want to talk to the last one, I know you were working mostly on.
Yeah. So I'll talk. Yeah. So just really quick about KubeVirt. So KubeVirt is another thing coming out of Red Hat. It's been around since 2016, I think, and it actually allows you to launch libvirt, virtual machines, but from Kubernetes, and you don't have to do the XML format or descriptor of the configuration. You can use the YAML format, and so it basically makes everything kind of. So for those of you who don't know, Kubernetes, it's all about these YAML files, and so all the examples he showed earlier, it's just all Kubernetes, YAML syntax, which is the more you get into using it, the more you want to have everything just be the normal Kubernetes way, right? It's like if we change everything from being Python and Bitbake to being 8 other languages, everybody get pissed off. And then finally about patchwork. So we added COS and PW client into the image that we're currently using, the container that we're currently using for building. And I've been using Patchwork client for my maintainer workflow of the layers that I maintain. So we've already proven that we can get the list of new patches from Patchwork and things like that. And we know we can do, PW client get AM to actually apply that into a tree and things like that. We just didn't have time to get all of this done. Literally, I've been doing this for maybe 2 weeks now. Trevor's been doing this for 2-3 months tops. So this is very, very, very raw, but we're very excited about it. And we've got a lot of ideas where we want to go. And we're looking very much for collaboration with other folks. And also, so shout out to Jan Luba, who's on the call. One of the ideas we've also got, instead of just doing QMU, we also want to run our tests on target. And we're discussing in the LabGrid community about perhaps launching with LabGrid. We know we could do it with Lava, but LabGrid is really intriguing to try as well.
Yeah, a big shout out to Conrad Shear too. I don't know if he's on the call. He's one of my colleagues at Wind River. He's been a big help in getting me going with all this stuff, in particular with the event listeners and everything, understanding that.
Yeah, and also, Paul Barker has done a bunch of interesting stuff in the cloud that I've actually been looking at, and then all the people that spoke today about containers, right? It takes a community to do all of this stuff. There's a dozen or more people involved behind the scenes in what we're looking at. And just one more thing I'll say, I mentioned the Living on Master talk that I gave. So go back to ELCE a couple years ago. That was an implementation I did at the time within Intel, and we were pretty happy with what we did with it. But as I said earlier about Jenkins and security issues, I'm not comfortable recommending it anymore, just like I won't support Python 2 anymore. Don't do Java, don't do MetaPython, or sorry, Python 2. So we were looking for something new, and at that time I wanted to use Kubernetes because we were already using Docker containers, the crops containers for the builds, but we couldn't pull it off, right? At the time, 2-3 years ago, Kubernetes was still pretty raw. We didn't have Tecton, things like that. And over the last few months, we've been talking about this, and Trevor was just excited enough to go off and throw his brain at this and solve some problems and get it working. And this is just us sharing what we are actually doing in our daily work now. So I'm actually building the YP Dev Day virtualization layer with Tecton now as well. So I think time for questions probably.
Yep. So that's the end of the talk. Yep.
Yeah. So Kevin Hellman's on, talking about kernel CI, right? They've switched their builds to Kubernetes, and he was actually one of the inspirations for a lot of this as well. And so we're now going to be working with them to try to switch their Jenkins integration over to Tecton. This is one of the things that I would like to help contribute to kernel CI. And I think also, Jan Lube, we've been talking about the testing stuff, LabGrid, maybe with kernel CI as well. And in my mind, I see all of this working together, and also scaling out to the cloud in massive ways. So let's say that you find a security flaw overnight and you need to ship a brand new distribution for 200 clients, 200 platforms tomorrow. How are you going to do that? Well, if money is no object, you just go throw whatever amount of money it is at AWS, and you go and you build all of this stuff in the cloud and deploy it. That's the power that this brings, and that's going to be hard to do in any other way, in our opinion. Any other questions or comments?
Joshua has a question. He has his hand raised.
Yeah, so this is really awesome. A lot of your CI configuration living with your code is a really popular thing right now. Is there plans to support that? Can Tecton support that?
So what
or
I'm
like,
actually getting, yep.
Go ahead.
Yeah. No, so I've worked with people that hate that. I personally kind of like it. And so what I'm doing with YP Dev Day virtualization layer, because it's not really what Trevor's doing with the Yocto Tecton layer, I'm actually putting Tecton into its own folder, just like I do with COS. And so my intent is actually to put those Tecton files there. We have some work to do to make it be a little more agnostic, because currently there's some like hard-coded paths and things like that. And we're a little frustrated with Helm because you can't dynamically generate things. And
Yeah, let
so
me
we're
see if I
looking at,
can give a brief just explanation of what I mean by that. So I'm going to enlarge this in a second. So looking at the pipeline run, so what I've run into, can everybody see this okay?
Yeah.
So what I've run into, I had tried, you can see there's actually a Helm chart available for the estate portion of this in the repository, but what I ran into is it doesn't like this, the generate name. So if you're not familiar with how Tecton runs, when you actually go and look at the pipeline runs as they're instantiated, there's a five alphanumeric character string that gets added to this to identify every pipeline run, but Helm doesn't like that. I'm not sure exactly why. I found an example and I've got it linked somewhere in the repository saying that's a problem. So I'm looking at alternatives. I'm looking at Tanka. I think Conrad is using Customize. There's a bunch of alternatives to it, but I haven't found a definitive one that will fix that. And maybe I'm just doing it wrong. Again, this is pretty new to me, but I've noticed it runs into issues with that.
yeah, and one of the things, just also kind of addressing Joshua's question is, so we're showing how to run kube control -F or create -F or apply -F with a file name, but you can actually use an URL. And so, I can literally go and set up the pipelines for any of our layers just by passing that URL to the kube control.
Oh, the URL of the Tecton pipeline?
Yeah.
Okay.
Yeah.
Okay.
So
which is really cool.
Because I'd
Go ahead.
imagine like in a more like corporate environment or something like that, not everyone's going to have access to directly create tasks in Kubernetes cluster, right? And so it'd be nice if you could actually control what the tasks, have someone create the task and then have what the tasks do live with your code, right?
Absolutely. And we really hope to get this to where, something that works, because Helm isn't working, would actually make this like a one-liner to set up the quote unquote cluster. I know Bruce is trolling us with it not being a cluster when it's a single node, but we really want this to be easy to set up and deploy, right? Whether it's bare metal or in a cloud. It's just, this is literally 2-3 months of work, right? You guys should be surprised we pulled this off. So it's been exciting, and we're really excited for where we're going to go with this next.
Okay, next question is from Frank. Go ahead and unmute.
This is great. I love this. You mentioned, doing everything on AWS. That seems perfectly viable. Some of us are just super lazy. Is there like a Tecton as a service? Is that offered by anybody yet?
I don't know for sure. I would expect that Google Cloud or Google Kubernetes Engine or somebody like that might start offering it or pick it up, or it might be easier to deploy there, or one of the Red Hat OpenShift offerings or something like that, or Azure or whatever. So we know that Kubernetes is agnostic, so all of those cloud providers would all be potential candidates. There's just more work that needs to happen there. We think if we can figure out something like Tanka, however you say it, to automate creating the cluster, that really it should just be, you know, this config map, or, you know, a file with your specific configuration in it, and the rest is just go and it's done. But we're, you know, we have not used AWS, we have not used the cloud. You know, we're doing this on our own dual Xeon build machines right now.
So Tanka, I know we're a little over time. What Helm does essentially is it lets you. So I'm showing an example again. This is a deployment that lets me view my S-state cache as an HTTPD server, and this is the Helm chart or the deployment. Sorry, for that. And so what Helm basically does is it allows you to do, you know, variable substitution in them so that you can customize things on the fly. You can say Helm install this chart and change this parameter or something like that. What Tanka does, which might, you know, in addition to possibly being a better alternative that like gets over the Tecton hump that we're having right now, what it also does is it allows you to do imports and create functions for specifying these resources. So it, you know, it will end up making your code potentially a lot more modular and easy to work with and port. But yeah.
Okay, any more questions? Otherwise, we should go to our break. Well, thank you so much, guys. That was excellent talk.
Sorry, I have one more question, if you don't mind.
Go for it.
Have you guys looked, is it possible, or have you looked at setting up an NFS server for S-state?
I'm sure it is, right? So let me just talk about S-state a little bit, because we've talked with Conrad and some others about it. You know, my naive idea was, hey, we'll just rsync it to S3, right? And Conrad's like, do not do that, right? It's so slow, it's going to cost you too much. And then I believe it was Paul Barker that was telling us about, you know, how expensive it is to do the networking, right? Because you're paying for everything coming in or whatever, right? So we're thinking you probably want to somehow figure out a way of deploying, you know, your S-state to a VM or something in the cluster, like right there next to it. And it's probably going to be better to do it with NFS or something like that. And we just don't know yet because we haven't tried it. So you know, we're just showing what we did locally, and everything is working, right? Which is kind of the amazing part. But there's a lot more to be done here, and you know, there's a lot of people. I mean, even like Michael Halstead knows a lot more about this stuff than we do, right? So there's a lot of folks that know more about the infrastructure and networking and things than we do. You know, we're just a couple of Yocto hacks. So, yeah.
Yeah, NFS S-state is definitely the way to go once you start scaling beyond 1 or 2 builds, because we're rsyncing now and it's like 50 builds and it's just murder. It's just insane.
Yeah. The other idea that we've been entertaining is, you know, doing the big build on your build machines that you might be on-prem, but then, you know, uploading a tarball to CDN and having that, or to S3, and then having that CDN around the globe to all of your teams and having them, you know, periodically update and things like that. Because in my opinion, the only way that the cloud model works is if you're using S-state really, really effectively, right? Because then you get 7-minute builds instead of 4-hour builds or whatever it is, right? So
yeah. And one of the things that we, you know, we had grand ideas for this talk before it happened, and then we realized we weren't gonna have time for it all. And one of the things we were talking about was showing off, adding, you know, fairly low power systems to your cluster, and then taking advantage of the S-state cache that was automatically built to show, hey, you can build this on a quad core machine in 7 minutes once the S-state cache is there, which isn't surprising to anybody, but the scalability and the ease of adding new machines to do those builds was going to be a stretch goal for the talk.
Okay, Emmanuel, why don't you go ahead with your question?
Okay, thank you. And I must say, I feel a bit ashamed by asking this question, but like for the beginners out there, can you just explain in really simple terms how Kubernetes and Tecton and Buildbot relate to each other? Because like many of us, or just I do have a bit of experience with CI, but I feel it's on a different level than what you guys are doing, because I'm just, you know, building my C++
Yeah.
and then shipping off the Debian packages. That's it. But Yeah.
Yeah, no problem. So I mean, there's a lot of different CI systems out there, right, and some proprietary ones and whatnot. So BuildBot is a CI framework where you describe your jobs and everything in Python. And then the Yocto Auto Builder has some stuff on top of that specifically for how we build things in our cluster for the releases. But there's also this, Yocto Auto Builder helper scripts, which is got some config that's in JSON format and some other things, some scripting and things like that. So that's just to get it running as the auto builder, right? So it's perfectly fine. It's very, very, very capable. We do immense amounts of work with it in the cluster. So as far as your other question, like how does Kubernetes and Tecton and everything relate? Just think of traditional CI mode, right? Like Kubernetes is just this thing that allows you to run containers, and Tecton is a way of describing things in CI terms with tasks and pipelines and things like that to the cluster or to those containers. And so it's basically just instead of writing things in shell script or declarative language or Groovy that you have to do with Jenkins, you're just describing them in these YAML files instead. So I know it's very confusing to you now, but once you get started with it, I found my brain melted down and then rebuilt itself over the weekend, and suddenly I got it because it's just basically the same concepts that we've all been doing forever with CI.
Okay, any last questions? Otherwise we should break. Okay, very good. We're going to break until 35 minutes after the hour. That's about 6 minutes. So we'll then continue with Matt. Thank you.
Thanks.
Okay, we have 1 more minute before we'll continue with Matt. Okay, it is 35 minutes after the hour, and we'll continue with our second to last presentation from Matt. Matt, why don't you go ahead?
Thanks, David. Hi, everybody. Hope you can hear me all right. So I'm Matt Madison. I'm going to talk a bit about the MetaTegra BSP, which is a BSP layer that I've put together over the last 5 years or so for the NVIDIA Jetson platforms. Let me talk a bit first about the Jetson hardware. And you'll hear the term Jetson and Tegra thrown around, and I apologize. It can be a little bit confusing. Tegra is the name of the systems on a chip that that NVIDIA developed, and Jetson is the name they gave to the modules that they built off those chips. So I tend to use the terms interchangeably, but technically there's a difference there. I'll talk about just the 64-bit Jetsons. I won't talk about any of the earlier ones because these are the ones that are currently supported. They all have a Tegra SoC, which has some number of ARM cores and an embedded GPU, and then some I/O as well, lots of I/O actually. The modules that they build include some peripherals, some memory, some storage as well. So the TX1 was the first. It came out in 2015. That was followed in 2017 by the Jetson TX2. This one is still currently supported. The TX1's been end-of-lifed. And you can buy a development kit that includes the TX2 module, as well as on a carrier board with power. And this one has Wi-Fi on it as well, and other stuff that you need to get going with developing with the Jetsons. The TX2 was followed by a TX2 4 gig model and a TX2i industrial grade model. More recently, in 2018, they came out with the Jetson AGX Xavier, based off their Xavier SoC that has a Volta GPU. This is their high-end unit. Includes 8 ARM cores of their own design. It's the Carmel cores, and lots of memory and lots of storage, and some deep learning accelerators. Then in 2019, they went low end, came out with the Jetson Nano, and that one has 4 gig on it, DRAM. They've come out now with a 2 gig stripped down model, which is roughly, I think it's $59 or something like that, to really target the entry level, sort of the Raspberry Pi type of consumer. And then midstream is the Xavier NX, which is based off the Xavier SoC, but is more targeted as kind of a replacement for the TX2. So they trimmed back the number of cores that they support. It has a smaller form factor, it consumes less power. It's actually some pretty powerful hardware, and it comes with a lot of software. NVIDIA provides a BSP that they call Linux for Tegra. And that's been around for a long time. It supported earlier revisions of the Jetsons and Tegras as well. Consists of a Linux kernel, all the bootloaders, the firmware, the drivers, power management stuff, basically everything you need to bring up the system. And then they also include that BSP as part of their overall Jetpack collection of SDKs and tools, which really is what most people are interested in that are using these things, because it gets you access to CUDA, CUDNN for for that's the neural network package, TensorRT for AI machine learning stuff, VisionWorks for their computer vision support, et cetera, et cetera. It's a big package of some big software. It comes with the tools that you need to get the software onto the device, which with the Jetsons, it's usually initially, it always has to be, in fact, initially flashed via a USB port. Uses special tools that NVIDIA provides, some are binary only, and there's scripts layered on top of that. It's very complicated because every single one of these modules works a little bit differently, and there's hacks all over these scripts to deal with all those differences. They do support secure boot on the devices, and there's additional scripts and tools that you need to have in place in order to be able to burn the fuses and then flash securely. So that's the BSP as provided by NVIDIA. There's the root file system that they provide for you to develop on is basically Ubuntu 18.04, which is maybe fine if you're going to try to set it up as a development station that you actually build natively on. But it didn't really fit very well, or doesn't fit very well into a typical embedded cross-build environment. As I was using back in 2015, when I first looked at this stuff, I was working at a company that already had a product. It was based on an IMX6 with some custom hardware for doing some computer vision stuff. We already had a Yocto-based distro that I was maintaining. And then I heard that the company was interested in possibly doing a next generation product that was based on this NVIDIA technology. So I bought myself a Jetson TX1 development kit and started looking at how I would adapt the BSP adapt their BSP into a Yocto style build. Then we definitely needed CUDA. We needed other hardware specific features from this stuff. So we needed to be tied to that hardware. But I didn't really feel like Ubuntu was a good base for doing an embedded distribution. So if you're going to do, so I decided to do my own BSP layer. NVIDIA wasn't interested in supporting open embedded Yocto style builds. They were happy with the Ubuntu offering they had. So let me talk a bit first about what a BSP layer typically provides. This is probably old hat for most of you, but it's the stuff that's board specific in terms of the kernel, the bootloaders, firmware, drivers. Typically have machine configuration files and any other board specific. So anything that's special about the images you need to create, board specific configuration files for sound or Bluetooth networking stuff, that kind of thing. And then often you'll see from vendor supplied BSPs, you'll see recipes for diagnostics or manufacturing tools. In Metategra, I've tried to basically follow that model. The kernel recipe in Metategra uses the kernel sources that are supplied by NVIDIA, which is a downstream kernel that looks like it comes from some Android products that they've been doing. They do provide the sources off a Git server that they host. It is a little bit unusual in that it's spread across about 15, maybe 16 now, separate repositories. So there's the core kernel, and then they have repositories for their drivers, the GPU driver, and a bunch of different repositories to host the different sections of their device trees that they have for these different devices. That was a little bit awkward to try and deal with from a recipe, so I came up with a mechanism using Git subtrees to basically reintegrate those 15 separate repositories back into a single repository that I host in a GitHub account. It's just a little easier to manage. for building purposes and maintenance. And then I try to keep as close to their kernel as possible. I have had to do some patches, mainly for building with newer versions of the toolchain than they typically have been used in the past. I think they were still using a 4.9 GCC to build things when we'd moved to GCC 7. So so backporting the necessary fixes for that from upstream, and then also there's always a few bugs, and so there's some bug fixes in there as well. These days we do use the in-tree def configs that NVIDIA provides. I originally had a per machine def config that was hosted with the recipe, but somebody convinced me to switch to using the Linux Yocto tools to do config fragment management. And actually that's worked out really well. I was a bit resistant to doing that at first, but just because I didn't understand how the tools worked. But once I got the hang of it, it's actually made maintenance a lot easier. For the bootloader, it's a little bit complicated. There's some binary only parts of the boot chain that have to be provided. They do support U-boot on some of the devices. The TX1s and Nanos and the TX2s support U-boot. U-boot doesn't really do very much other than locate the kernel and the rootfs to boot off of. It doesn't really do much in the way of hardware setup. That's all handled now. It used to, but these days is all handled through NVIDIA's C-boot bootloader, which is the actual secondary bootloader, and then U-boot is a tertiary bootloader. The U-boot support, they used to have an old downstream fork that they ship. They still ship from there, but somebody at NVIDIA has actually upstreamed all of their changes into U-boot mainline. So the latest recipes actually can track OE core more closely. The C-boot bootloader is NVIDIA proprietary, but they do publish sources for that sometimes. So if you do need to do some customization of what C-boot does, you can get the sources and do that. You just have to be careful that as they upgrade the BSPs, the C-boot releases to match that tend to lag. The machine configurations in Metategra, basically, we've got configurations for all of the development kits that NVIDIA offers for these Jetsons, plus a few more for some of the non-dev kit modules or modules that are plugged into the development kits that aren't the standard ones. Because each of the modules uses a has a different family of chip. I do make use of the SOC family support to try and group packages together and overrides together that are specific to the SoCs that might be common across multiple modules. And then recently added overrides for Tegra and a Tegra package arc for packages that are common to all of the Tegras regardless of which SoC they're using. It's complicated. And then as far as imaging and flashing goes, this was the hardest thing to get right. Just because it was hard to sort of reverse engineer how the NVIDIA scripts worked, but and plus the workflow is a bit different. The NVIDIA flashing tools assume that you pretty much assume that you can talk to the device as you're flashing, and then maybe make tweaks to the root file system and then send it over. Whereas for Yocto builds, we basically have everything available, everything built into the rootfs before we're done, and we can't do any talking to the device in between. So there is an image types BB class that creates a package called a Tegra Flash package. It used to be a zip file, now is a tarball that basically puts everything in there that you need in order to be able to flash the target. And then it's complicated by the fact that these modules come out with different revisions And there's certain configuration files or device trees that are specific to the different revisions. And you need to know when you're flashing the device, you find out which revision it is, and then you send down the right version of those configuration files. It gets a little bit hairy. So these Tegra Flash packages can be pretty big in terms of the number of files in them. For the devices, for the dev kits that have SD card slots, you can use the Tegra Flash package to generate an SD card that's plugged into your build machine, and then take that SD card and plug it into the Jetson to boot it up. You just have to be careful about the bootloaders in that case. There's also additional handling for things like signing the boot components when you've got secure boot enabled, and for handling bootloader update payloads. They have a mechanism for doing what they call OTA updates, which is they provide a tool that runs on the device that takes a package in a particular format, picks out the right bits of the boot chain that need to be updated, and then sticks those in the right places, which would either be an eMMC boot block or QSPI flash, depending on which module you've got. Also, recipes in there for firmware and other services that support talking to the hardware. These things have very complex power management, and there's daemons that need to run to help with power management of the hardware. There's also some what they call driver libraries for dealing with hardware from userland, where they don't have necessarily all of the smarts down in the kernel, and then a daemon for talking to or for getting input from cameras through their ISP that knows how to control the ISP. Graphics support's another complicated piece because, of course, this is NVIDIA. So they don't. So the typical, Mesa and for OpenGL and the stuff that everybody else uses. Of course, we can't use that. The SoC does have a GPU and CPU combined, and they share the DRAM. The GPU driver is provided in source form in the kernel, but some of the userland components are binary only to deal with some of the special NVIDIA sauce there. There's a libdrm.so shim, and then they use the libglvend API and plug in their platform, their vendor-specific OpenGL provider under that. And of course, there's a special Xorg X server driver. There is some support for Wayland using the EGL streams patches. I can get West and Up. They use the EGL Wayland support that they developed. I think they still consider it experimental at this point, but it does work. And then they do have some Vulkan support, at least if you're using X11. And then on the multimedia side, they provide plugins for libv4l2 and for GStreamer for handling video streams from the cameras and to generate GL surfaces, mainly to deal with handling their NVIDIA memory buffers. They also have a specific multimedia API SDK for the Jetsons. It's just a bunch of headers and some sample code. The libraries themselves are part of the BSP. And then there's Jetpack. So we, since people are using Metategra, are apt to need things like CUDA and so forth. There's a bit more than just a BSP in here, in that we also have recipes for basically unpacking the Debian packages that NVIDIA provides for their SDKs and repackaging them for the Yocto builds. CUDA is a little bit more complicated just because there's the host side tools as well. And the idea is you want to be able to build CUDA applications, cross-build CUDA applications. So there is a CUDA BB class in the layer so that you can configure and cross-compile CUDA applications. It does create some additional, there's some CMake modifications or some modules that are added to help with that. And it took a little while to try and get SDK support in, but that's there now as well. So you can build an SDK and have it have the NVCC be in there and all the CUDA support, and have it just have, if you've got like a CMake based application, like say OpenCV, for instance, you want to add CUDA support, you can do that either through a bitbake recipe, and we do have a BB append for OpenCV that enables CUDA support. You can also create an SDK and cross-build your CUDA application that way. There are some dependencies on the toolchain version. If you use CUDA, CUDA only supports current version that they ship with the Jetson, only supports up to GCC 8. So that is a restriction you have to deal with if you're putting together a distro where you want to use this. You do have some virtualization support as well. That was added in revision 32 of Linux for Tegra, and thanks to contributions from Wind River, we got recipes in there. It will you can actually build the NVIDIA Docker support if you have the meta virtualization layer in place. And there's some Jetson specific container runtime pieces that need to be in place to make this work. For the Jetsons, NVIDIA decided that because the Jetsons by themselves don't have a whole lot of space, and some of the CUDA and other application libraries are really large, in order to save space, the Docker containers that NVIDIA builds for the Jetsons that are available from their NGC download site take advantage of the fact that their container support does a bunch of automatic pass-throughs from the host into the container of some of the core libraries. And so things like CUDA, TensorRT, a lot of stuff that's generally pretty big and would be really large to download into a Docker container, they're passed through from the host. But that means you can only run certain versions of the containers on certain versions of L4T. In order to help with some of the version compatibility problems, particularly around the tool chain, we added a contrib layer that's optional. You don't have to use it. You can, if you've got a way to build the older tool chains that you're already using, you can use that. But these recipes, basically forward ported from an older version of OE Core, are there so that you can have GCC 8 available easily. And likewise, for GStreamer, their Docker containers, because it's they're Ubuntu, they assume Ubuntu 18.04, that's still at GStreamer 1.14. So since OE Core has moved on from there, you may need to build the GStreamer 1.14 in order to be able to support NVIDIA's Docker containers. And likewise, their DeepStream SDK, which recently was contributed by folks from RidgeRun, recipe for that. We ran into an issue where there was some compatibility with some of the binary-only components of the DeepStream SDK needing GStreamer 1.14. So we got recipes there to help with that. So this has been an interesting 5 years, and maintaining a BSP layer has been fun, but it's been a lot of work. It's helped that I've had real products at my day job in order to be able to give the BSP a good workout. Of course, it hasn't covered all the platforms, but at least it's given me a good way to test whether the BSP layer is suitable for real production use. I've been, and if one of the things that I've tried to be good about is tracking master OE core. And with the master branch I have and the BSP layer, that's been really good in terms of being able to deal with things like toolchain upgrades and other or graphic stack upgrades for which I needed to adapt. Doing those a bit at a time and tracking master along the way has made that a lot easier. I know a lot of folks tend to stick at a fixed long-term support version, for instance, for a long time and then move over. I've done that for other projects in the past and have found that tracking the latest usually works better in terms of incremental effort involved in keeping up to date. I also have been trying to be really good about sticking as close to the stock settings from that NVIDIA provides with their BSP and not making gratuitous changes. And that's been good in terms of trying to track down when issues do crop up, whether it's an issue in the original BSP or whether it's something that happened in the layer. I do have automated builds set up. I've got my own AWS set up, and I do all my builds in the cloud. I do those automated with some test distros I have set up, and that's been helpful. I could do more if I had money to do that, but it's been enough without being too terribly expensive. It's also really helped me to have supportive employers that have been that have let me do this stuff, even if it wasn't directly related to my work. But I've also learned a lot. This is hard. I know that I hear a lot of complaints about how bad BSP layers are, but they're really hard to do well, I think. It's easy to get focused on making sure that your platform works, and it's easy to forget that there are other machines and other architectures out there. One thing that I didn't know about until just earlier this year, back in the ELC North America, was the first I'd actually learned about the Yocto check layer script, which I don't know why. I've been using this stuff for almost 10 years now, and I never ran across it before. But it's been a big help in terms of trying to catch mistakes, even though I've tried to be good about playing nice with other layers. It was a real helpful in tracking down some things that I thought I'd done right and hadn't. Putting machine-specific settings in machine.conf files. I started out when I did this as I wound up using a lot of overrides in recipes. And that worked okay initially, but really it gets harder and harder to maintain over time. So I try to consolidate things into the machine configuration file. So when I have a new machine I need to bring in, because there's a new model, I've got all the settings right there. And that makes things a lot easier. Trying to keep the layer dependencies to a minimum with Metategra. It's only dependent on OE core. There are a couple of places where being dependent on Meta Open Embedded maybe would have made things a little easier. I think I know at work it's worked out better to just have the core dependency, and I think other users have found that to be the case too. It also helps with keeping the number of permutations, combinations that you have to test against to a minimum. And then using existing infrastructure. When I first started out, I didn't worry too much about how the kernel recipe worked or how the U-boot recipes worked. But it certainly makes it easier to use the classes and the include files that are down in the core layer to provide some infrastructure for getting your builds to work. And it just makes things a lot easier for folks that are used to the way those recipes work for other platforms. And it's also, the other thing I learned is the way I build things, my workflow, my configuration, whether it's at work or for my hobby work here, isn't the only one. Again, you get focused on getting your work done, and it's really hard to keep in mind that folks use this stuff in a lot of different ways, and a BSP layer needs to be able to work with, you know, if somebody's really fixated on sysvnet, it's got to work with sysvnet, even if NVIDIA only supports systemd now with their BSP. The different packaging formats, SDK builds, there's a whole bunch of stuff that hopefully your BSP layer isn't affected by, but where there are touch points, you got to keep those in mind. As I said, these are powerful little devices. There's a lot of software available for them. They're complex. It's an ongoing challenge to deal with all that. Each platform is a little bit different, sufficiently different that sometimes it's difficult to make a change without breaking one of the platforms, so you have to be careful about that. The BSP itself from NVIDIA, their release process, let's just say could be a little bit more rigorous, run into regressions and just general quality issues, particularly with the tools from a release to release. Their support is through a forum, and you can, if you harass them enough, you can get them to provide fixes, but what they'll do is they'll just post something to the forum. They've started collecting those on the elinux.org wiki, so you at least get links to patches that they have for the problems in their BSP. But it can take several months before it actually works its way into a new release, because these are big bang releases with supporting all the platforms, and typically they rev all the Jetpack stuff at the same time they rev the BSP. Not always, but sometimes, most of the time. And then just keeping on this old downstream kernel with the Android patches and then NVIDIA's patches on top of that, the binary only problem, and the toolchain version issues. It's been a challenge over the years to manage that, and I'm sure that will continue to be the case. Although I'd say NVIDIA has at least released more sources for more bits of the BSP over time, and hopefully that's a trend that will continue. And then this whole dividing line between what's a BSP and what's really application support and what really belongs in a BSP layer. That's another open question that I've had in mind here lately. So, and you really can build a BSP layer of your own. It's not a small task. The Jetsons are some very interesting and some very capable hardware. I mean, I'm working for a company now that's doing facial recognition type stuff so needs machine learning and AI. The hardware is well adapted to those kinds of applications. You don't have to use NVIDIA's Ubuntu-based software distribution if you don't want to, although NVIDIA doesn't seem too keen on supporting anything else, although they have partners now that will actually help with doing Yocto support for you. But if you're interested in the hardware and you're interested and you can live with some of the restrictions that we have with the binary blobs and stuff, it's got the Metategra layer to help you out. What's next for the layer? It's been mostly, if you look at the history of the layer on GitHub, we have multiple contributors, but I think my contributions are like 2 or 3 orders of magnitude higher than anybody else's. So I'd really like to get more active developers involved. We could use some more documentation on the project itself and how to use it and so forth. Love to add content. Love to make it easier for for new folks to get started. And in fact, with the help of Dan Walks and Kurt Kiefer and some other contributors, we have a reference distro now, a demo that you can just clone and have a build set up that will build some images that have all the necessary bits in them to exercise some of the cool stuff that we've got with this hardware. So if you're interested, please get in touch. You can find us on GitHub. We have a Slack channel for OE4T. There's an invite on the wiki for the Metategra layer that will let you join automatically, or reach out to me by email. My email address is here. So thanks very much.
Okay, we have 15 minutes for questions. Please raise your hand for the question and unmute. So Frank, why don't you go ahead? Frank, you can unmute.
Sorry about that. So I have a Jetson Nano right next to me, and I have, played with the jetpack. It works. But what I would love is just to have a Jupyter server run, and I would just open up a browser window on something else and start doing stuff in a Python notebook, and all the GPU support would just work. I mean, that would be my dream. Would this layer be able to build an image like that?
To say the truth, I don't know enough about Jupyter to know whether it would need anything that requires access to the GPU. If it goes through APIs that NVIDIA already supports for their x86 with the discrete GPUs, it's likely to work on the Jetsons.
You mentioned their Docker images and how those are able to tap into the GPU. Does that require like a special Docker engine, a special build of that, or?
Yeah, and the support's in the layer to pull in the NVIDIA container runtime support that's needed.
Fantastic, because that's the other thing you want. You want all these ML libraries in your Jupyter notebook, and it's I don't imagine you can just install Conda on this thing and start installing packages.
It's the other issue, of course, is that a lot of these libraries, a lot of these packages get really, really large too, and just the time it takes to build them and the space it takes up on the flash, it can be pretty hard to do if you're building from source all the time. So I can understand why people want to use the containers, and any of the NGC containers that they have that are tagged for Jetson should, if you run a Yocto image and you've got if you use, for instance, the demo image full that we have in our demo distro, that pulls in all of the application support, and that will all be there, so that any of the containers that need any of the CUDA stuff or the TensorRT stuff, any of that stuff, should just work. And I patched the NVIDIA container runtime support to deal with the fact that the containers are expecting everything to be in Debian style multi-arc directory structure versus what we have with the Yocto build. So that mapping happens automatically.
Thank you for that. I know this must have been a tremendous amount of work. and it's very much appreciated.
You're welcome.
Okay, our next question comes from Jeff.
Oh, hi, Matt. Thanks a lot for all the tireless work you've put into this for the last 5 years. Really appreciate it. My question is more like on, support for from NVIDIA, and I'm just still surprised after all these years. It's not better than it. Just the Ubuntu distribution, and you mentioned just the form support. Do you see that getting any better or any more interest from NVIDIA in supporting Yocto, from their end? Because it seems like with automotive, medical imaging, this is a natural fit that they would want. They would want to use the best embedded system development tool to be championed.
I can't read the minds of the folks at NVIDIA. I will say that they do have partners, and I don't know if anybody from like Ridge Run is here. That have been designated as, okay, if you want Yocto support, you can pay these people and they'll help you, and they'll have there's different levels of partnership that NVIDIA has, and depending on what level you're at, you get more or less contact with real people, real engineers on the inside. So if you've got a partnership arrangement with NVIDIA, if you're a customer of theirs and you sign some kind of contract, you can get access to better support than you would get through the forum. Or you can deal with one of their designated partners that can do that for you as well. But to be honest, I was at one of my previous employers. We did have an arrangement with NVIDIA, and I did have direct access to their inside support. It really wasn't much better, to be honest, for the kind of stuff that we were looking at. There's a lot of stuff that that you got to figure out for yourself, unfortunately, or find somebody that knows this stuff that can help you. But yeah, as far as the Ubuntu distributions go, that seems to be the direction. It seems to be, from the marketing stuff I've seen from them on this stuff, they're calling it the Cloud Edge or something like that. That basically they're so focused on the GPU based, the compute stuff. I think their intention is you just run Ubuntu on these things, and put all of your applications in containers that you drop down there, and that's the way you support these devices. But it just doesn't fly for the kinds of devices I build, and probably that most of you build either.
Okay, if you have a question, please raise your hand. We have a couple of nice comments in the chat from Leon and Manuel. Thank you for your great work.
Thanks. And thanks, Leon, I know Leon did a talk about using Metategra at a previous ELC or Yocto Dev Day. So thanks, Leon. And Nico's, yeah, I know Nico. I've dealt with Nico with you on MetaQCOM. I submitted some patches to MetaQCOM some years back too, because I have also worked on a Qualcomm-based project. And yeah, I don't envy you that either. Qualcomm and NVIDIA are two peas in a pod, as far as I'm concerned.
Yeah, I remember your patches.
All right. Well, thanks, everybody.
Thank you very much. So we have 7 minutes till the next talk. So let's take a brief break and we'll resume at 25 minutes after.
So.
We'll be starting again in about 2 minutes.
Can you hear me?
Yes, I can.
Okay, thank you.
One more minute, and then we'll start. Okay, Verizon Standard Time tells me it's 25 minutes after the hour. So, Norbert, why don't you go ahead and get started?
Okay, thank you. Hello, my name is Norbert Kamiński, and today I will tell you how to create a partition image with the Wits custom plugin. I will also tell you some tips and tricks based on the boot image grab trench boot plugin development. So let's start with the agenda. At the beginning of my presentation, I will tell you a few words about myself. Then I will go to Open Embedded Image Creator, and I will tell you how to prepare the layer to build the custom partitioned image. And I will tell you how to create a weak Kickstarter file. So in second part of my presentation, I will tell you how to create a weak custom plugin. I will present you some overall information about whole interface, and I will speak about plugin source methods. Plugin source is the class that contains the methods of weak plugin. At the end of my presentation, I will show you my story of development, boot image grab trench boot. That's a custom weak plugin. So at the beginning, let's answer the question, who am I? My name is Norbert Kamiński, and I'm working at 3MDEP System Consulting as embedded system engineer. I'm contributing to open source projects such like Meta PC Engine layer, Meta Trenchboot layer, and my last project, open source project, was connected with Cube's operating system. I was developing the wrapper for firmware update system. So in my scope of interest are bootloaders. I'm also interested in embedded Linux, and I'm a huge enthusiast of virtualization and containerization. In the first part of my presentation, I will tell you some information about the Open Embedded Image Creator, WIC. So what is WIC? WIC stands for Open Embedded Image Creator, but you may ask why it's W in this acronym. So documentation says that OE would be too hard to remember and too hard to pronounce. So let's stay with WIC. It's used to create a partition image. It's loosely based on MIGO image creator framework, but the main difference between WIC and MIG is that WIC is building the partition image from the artifacts that was built before. It's not installing the packages and custom configurations. So how to prepare your layer to create the custom partition image. At first, you have to go to your layer and you have to add to the local configuration file the WIC, just WIC interface variable. So as you can see here, we have image fs type variable that should be in local conf file, and we are adding a WIC to it. So the next thing which we have to decide is if we want to use the existing Kickstarter configuration file, which contains ready-to-use prepared partition layouts for devices or for the platforms, or if we want to create our own partition layout. So if you want to choose a ready-to-use partition layout, it's good to know what we have to choose for. So at the start, we have to source the script in Pocky repository, and then we can list the images names, the partition layouts names with this command. As you can see, we have plenty of configuration files, Kickstarter configuration files, which we can choose from. So if we found the right partition layout, we have to add the Kickstarter file to our local configuration. But if we want to create our own Kickstarter file, we have to again go to our layer. Then we are creating the weak directory, and we are creating the weak Kickstarter configuration. So we are creating the short and long description for our partition layout. And we are specifying the custom partition layout. So let's start from the beginning. As you can see here, we have part command, which creates partition and takes the takes the mount point as input parameter. And the first partition is boot partition. So we are creating the partition that will be mounted at boot. The second parameter is the source. That specifies the particular weak plugin that will be used to create the partition. Next parameter will be on the disk. That parameter force creating the partition on a particular disk. And we have FS type parameter, which sets the file system for our partition. Okay. Next will be label that name our file system. And it could be used to boot proper partition. It may be used as the parameter in bootloader, like in grub configuration, you may pass the root fs a1 and it should be booted, as you can see as root fs. Okay, so the next parameter will be active. It sets the partition as bootable, and the lane specify the maximum size of boundaries between the partitions. Fixed size sets exact size of the partition in megabytes. Okay, the last thing you have to done in your weak Kickstarter file is specifying the bootloader option. You are specifying the partition table type, you are specifying the timeout of the option, and you may append the command line in your bootloader. So once you have created the your weak Kickstarter file, your partition configuration, you can list again the available Kickstarter files, and you will see your partition layout with your short description. So here we have some development tips. First, development tips will be about debugging the partition layout. You don't need to flash the device to check if the partition layout is correct. You can use for this purpose low setup command. And when you just mount create loop device, it prints the device that has been created. So if you list partition layout from this loop device, you will see if everything is correct. and you may mount the particular partition and see if the files that you have populated to this partition are that one you want to. Okay. The second development tip is about speeding up the flash process. So you don't have to use the dd command. It's a pretty slow command, and if you want to speed up the flash process, you may want to use the beamup tool. So at first, you have to, again, add to image fs type variable in local conf file the weak beamup and compressed weak file. So as you can see, we will have the beamup file that describes the compressed image. And you need to use the root privileges here, and you may want to copy the your image to your device. So using beamup tool speed up the flashing process by 5 to 7 times. Okay. So the second part will be about the weak plugin interface. What is weak plugin interface? It provides the mechanism to customize the image generation process. As you may remember from the previous part of my presentation, there was a source parameter in a weak Kickstarter file. That parameter specify the weak plugin that creates the particular partition. So the source plugin are subclasses based on the source plugin class, which is defined in the POCU repository in following Python script. Okay, so weak plugin could be defined in your meta layer. Again, you have to go to your meta layer and create following directory, and then you have to create Python script, which will have the name variable that will be the same as the source source parameter that you pass in your weak Kickstarter file. Documentation says that the Python name of the Python script should be the same as the name of the variable. So that's you may want to name your Python script in a different name, and that's okay, and it will work. But it's preferred to not do that. Just stay with the name that you have defined here. Okay, now we are coming to the plugin source class and its method. So every weak plugin that you are writing will have a few standard methods. The first method you will use is to configure partition. That method creates the custom configuration files for a partition. It may takes the custom configuration files from the build and populate it to the partition. The second method is stage preparation. That method allows to stage the partition files in the customized way, and typically it's empty. I do not use this method in my weak plugin. So next method is do prepare partition. Method does the content population, so it prepares the files to be incorporated into the final image. And we have do install disk methods which finalize the disk image creation. It could write the master boot record, for example, the boot image from grab bootloader. So next will be do post partition. That method allows to execute the post operation after the partition is created. It could be used to the security purposes like signing the partition. And that's the third part of my presentation. It will be about the development of weak plugin. So one day I came to my office and my team leader asked me to create a partition, boot partition for the trench boot. At start, you may ask, what is the trench boot? It's a framework that allows the individuals and projects to build security engines to perform large integrity actions for various systems. That sounds a little intricate, so you may want to use our layer meta trench boot, which creates the ready-to-use builds that provide dynamic root of trust measurement for UEFI and PC BIOS platforms. And we have a third bullet, my plugin, that's boot image grab trench boot plugin. It creates the custom boot partition for the trench boot purposes. Okay, here we have the group boot process on the PC BIOS platform. The boot partition of the trench boot is based on the grab, and I will describe you the boot process of for PC BIOS platforms. At the start, we have BIOS, which selects a hard drive and reads and loads the boot image. The boot image is written to master boot record, so it's the first sector of the partition. It contains the logical block addressing of the first sector of core image. Its task is to load the core image and transfer the control to the core image. Core image contains the loader addresses of the blocks that allows loading the core image to the memory. Once it's done, grab kernel takes over initialization. So if we are in that point and something goes wrong, now grab will throw the rescue shell and show us some debug information. So from this point, we are pretty aware what is happening with our grab. So the next step which grab is taking is loading normal module. So normal module should be installed in the module directory in the boot on the boot partition. And when it's loaded, it runs the normal command that display the grab menu with the grab configuration file. Okay, now we have here architecture of weak plugin that I have developed. It contains three methods of the class I've mentioned in earlier of my presentation. First method will be deconfigure partition. That method contains the copying custom grab configuration file if it exists. If not, it checks the deploy directory and it's checking the files that are consist in this directory, and then it creates the grab configuration. So if we have a hypervisor there, it will create the multi-boot command line. If we do not have the Zen hypervisor, it will be just a standard command line of the grab. Okay, so next is copying the custom grab environment file that contains the environment variables that may be used to provide the update for our platform. So next method is to prepare partition. It populates the boot partition with kernel files, with custom grab modules. Custom because we are copying the standard grab modules, but there are also modules which enable the secure launch in grab. So it is checking if Zen hypervisor exists, and if it exists, it copies the Zen to the boot partition. And at the end, it installs the grab core image. Last method in this weak plugin is the install disk. It installs the standard master boot record, and next it installs the boot image to master boot record. There was some challenges during the development stage because when we are trying to install the boot image to master boot record, it's not so easy when you are doing this into file. When you have a physical device, it's easy to recognize what is the root partition, and that's pretty easy. But when you are installing the image to the file, you have to work around this with additional parameter because the standard grab bias setup is not cannot guess the root partition. So we work around this problem with our parameter that specify the root partition. As you may see at the snippet, it's here. Full source code of this patch is available at the following link. Okay, and some development tips for weak plugin. When you are creating your weak plugin, you want to usually you want to use some custom or standard variables from the bitbag. And there are two ways to pass variables to the weak plugin. The first way is to obtain a bitbake variable by using the get bitbake var. As you can see here, I'm just taking the bitbake variable and I'm writing it to Python variable. The second way of the passing variables to the plugin is to use the source params. That's the parameter of weak Kickstarter file. It takes the name of the parameter and its value. So if you want to obtain this parameter in a weak plugin, you just use the source get params. As you can see here, we are obtaining the init rd. Okay. So during the plugin development, you may need to use the parameters of source plugin methods because it's easier to populate the partition with these parameters. So CR workdir is the work directory of Wig, and it contains the creator artifacts before they are deployed to deploy directory. The HDD dir directory is used to populate a partition. So the files are copied there before they are installed into final partition image. And the last parameter of source plugin method is kernel directory. It's typically equal to deploy directory of your build image. And it could be used to custom the kernel that you want to install to your partition. So thank you for your time and your consideration.
Okay, very good. Very great. Excellent presentation. Thank you. So
Thank you.
please raise your hand for any questions. There is one hand. Does anyone know if we can use WIC with IPXE and do an install with no human interaction?
Wait, maybe I will stop the sharing my screen and
yeah, check out the chat.
Easier. Yeah, okay. Okay, the question is, anyone knows if we can use Wig with iPXE and do an install with no human interaction? So we are building the Wig images for Initram FS builds, and we are using these builds with iPXE. Maybe I will share something more. Wait a second. So it could be here. Okay. So as you may see, as you can see here, we have here a method range player, and here are the Initram FS cast configuration file for the our build. So we are using this build with our iPXE images that leaks in on our FTP server. Something like that. Or not like that. Yeah, that's the FTP. So we are having here Initram FS images, and we are just downloading them by iPixie, and we are booting our images. So there are, we have a flashing image, which contains the tools for flashing another images on the hard drives. And we have pipeline failed, yeah. We have the standard image, which contains standard distro to use. And can we do that with no human interaction? I'm not the expert with the automation, but our automation team is using the robot framework that use our IntraMFS images to flash the standard standard images to the disks. Okay, any more questions?
Please raise your hand so we can unmute you. Did you address the GPT question?
With Kickstarter GPT support. There is, I think, GPT support. Once again, I will share my screen with the browser. Wait a second. Where is it? Okay, here is it. Let me take my notes. We have here. So I will attach maybe the fragments of the documentation where they are described with plugin and with Kickstarter file. And we may use GPT. As you can see here, the GPT is available for our bootloader. And I think that's the answer for this question.
Could you define GPT for those of us who do not know?
Once again, can you repeat?
Could you define GPT for those of us who are not familiar with that term?
Yeah, sure. I do not want to. Okay, that's GUI ID partition table. Polish Wikipedia. So here we are. I can send to everyone. Okay, any more questions? So once again, thank you for your time and for your consideration. And if you want to contact me, just click on the one of the links that are attached to the logos.
Thank you very much. That was an excellent presentation. Okay, this concludes the first day of the Yocto Project Summit. We're going to take a break for 10 minutes and then invite you back for an open mic. And we can just gossip and talk about things about Yocto Project. So thank you so much. See you in 10 minutes.
And I will stop the recording so that anything can happen now.
Thanks, Nico.
I know you read that, Flip.
Yeah, I did the same thing in the beginner class.